You ready? Okay, good, thank you. Okay. All right, good morning. So yesterday we were talking about indexing EBSD patterns. Good morning. And we showed how to, once you knew the angles, we showed how to go through the lookup table and determine what's the correct solution. We haven't talked yet about how to get the correct angles, and we haven't talked about how to get orientation, the mathematics behind it. So that's what we're going to start with today. All right, so pattern center calibration. This is showing the geometry of an EBSD system. Of course, your specimen's typically tilted, although it doesn't have to be tilted. You can get EBSD patterns with its flat, but typically it's tilted. The camera, the detector, EBSD detector coming in can be at an angle like is shown here. It could be coming in straight. Sometimes it's coming in at a negative angle. None of that really matters. What we're looking for the what we call the pattern center calibration is to know the position normal to the phosphor screen or normal to the EBSD detector that is the closest distance to the specimen beam interaction volume. So the normal, we want the position that's normal to the phosphor screen that intersects the point where the beam hits the specimen. So that is a definition of our pattern center. It doesn't have to be in the center of the EBSD pattern. It just has to be in the plane. It doesn't even have to be on the visible pattern itself. It could be off of the screen completely. So it's just a mathematical entity that we're looking at. All right, so that pattern center, obviously, if we have a short working distance, it might be up near the top of the detector, the phosphor screen. Working distance increases, that pattern center comes down, right? Longer working distance, maybe it's down towards the bottom. So that pattern center changes as working distance changes. It's not a fixed entity. So usually what we do in setting up the calibration, how your systems are set up, is it's basically set and we say, okay, at 5 millimeters working distance, what's the pattern center? At 10 millimeters, what's the pattern center? At 15, what's the pattern center? And those are included in the software. And so once you tell it what the working distance is, then it will know what the pattern center should be. And there's nice equations that show that. We define this in coordinates of the phosphor screen in an X, a Y, and a Z, and we usually put a star on it. X star, Y star, Z star defines our pattern center. The Z star value is this specimen to screen distance. So that's the shortest position from where the beam interacts with the specimen to the plane of the phosphor screen. Okay. If we're close in calibration, then we can tell the software to look at the bands that it's found and tune the calibration. So we just can click a button and it will optimize the calibration. Usually what we're looking for to optimize the calibration is looking at that fit parameter that we defined yesterday, making sure that's less than a degree. Assuming we've already looked at the Huff transform and we know that we're finding all of the bands properly. Okay, the other thing we calibrate is for the millimeters on your specimen, translating that to millimeters on the phosphor screen. So if we take, you're in one corner of a crystal, for example, you move to the other corner, your pattern center has to change by that same physical amount. So looking at the phosphor screen then, you can say my pattern center's moved from X equals 22 to X equals 41. It's done that over 3 millimeters that I've clicked, so then I know how many pixels on my phosphor screen translate to how many millimeters or how many microns. So that's another important calibration that's performed. In the old days, so in the 80s, we used a silicon single crystal. It was a 100 oriented silicon wafer. So the polished wafers that are used to make computer chips. So there's a lot of them around. if you cut that wafer, if you cleave it, it's going to cleave along the 110 plane. So you have a 100 pointing out and a 110 along the cleavage plane. If you align the cleavage plane in the vertical direction, so as it's tilted down the axis, your tilt axis, then this dashed line in the middle is the 110 plane. Okay, so the EBSD pattern shown here, that's the 111 plane. This 114 position is 19.4 degrees away from the 001 position that would be up here in the phosphorus, in the plane of the detector. So that means if we tilt at 70 degrees, if we tilt the specimen at 70 degrees, then the 114 zone axis will be exactly at the position of the pattern center, right? Because your specimen's tilted 70 degrees, your 100 is pointing out, 20 degrees down from that, along the 110 is the 114. So most of us, when we do EBSD, we work at 70 degrees tilt, right? You can work at 60 degrees. You actually get better contrast if you go up to 80 degrees tilt. The reason we work at 70 degrees is because we used to always put in this silicon calibration sample and say 114 is where the pattern center is. So click on that, that's the pattern center, and then we keep that 70 degree tilt. But it's easy to work at any other angle, so we don't have to be at 70 degrees. That's kind of a leftover from how we did pattern center historically, right? But if you ever want to check, it's easy to throw in a silicon single crystal, cleave it along 110, line it up, look, and your 114 should be in the position of your pattern center if you are tilted at 70 degrees. Okay? All right, so what we typically will say is we want this geometry so that the pattern center is about 1/3 the diameter down from the top of the phosphor screen. The reason for that is at 70 degrees, your backscattering is going to be more prominent in the lower part, right? So it's your electrons are going to come down and they're going to forward scatter into this position. We want the maximum intensity of our scattering to be in the middle of our detector, in the middle of the phosphor screen. Now, exactly where that position is going to depend on the backscattering coefficient of the material. So as you switch from aluminum to tantalum to steel to titanium, you're going to have a little bit different position that would be the ideal working distance for your specific specimen. But you can play with that, and as you look, if you don't do a background correction and you're just looking at the intensity of the phosphor screen, you want the highest intensity to be right in the center, instead of, looking down here, up here with it. Okay. So this shows the coordinate frame, X and Y, and then Z is presumed to come out, of course. And the Z, when it's coming directly from the pattern center, that's your specimen to screen distance, right? Okay, now we've talked about using EBSD to measure the D spacing. And we said that as you have a diffraction pattern and you have these two diffracting cones, so you have one cone off the top of the plane, one cone off the bottom of the plane, and they create these lines. So that's a Kikuchi band. The distance between those, that angle, which I'm calling beta here, is 2 theta from Bragg's equation, right? So that angle is 2 theta because you have diffraction coming off the top of the plane at an angle eta, and you have theta, and diffraction coming off the bottom of the plane at an angle theta, so the distance between those is 2 theta. So that angle is 2 theta. So if we're going to try and measure D spacing, now these are parabola, right? So the distance is different depending on where we are. But if we start with the pattern center and draw a normal to where those bands are, to where the center of that band is, that's going to be the actual 2 theta angle that we're looking at. Okay. So if we measure it over here, it's going to be incorrect. If we measure it over here, it's incorrect. But if we measure it coming out at a normal from the pattern center, right, that's what that square there shows, that this band is normal to the line coming from the pattern center. If we measure along that length, then we should be able to measure what the 2 theta angle is. from the diffraction. Now, we don't measure it very well, right? Because there's maybe 30, maybe 100 pixels, if you're lucky, between these two bands. So maybe we can measure it to within 1% or to within 5%, something. And if we're trying to measure elastic strains, we want to measure a fraction of a percent, right? We want to go to 0.1%. So very difficult to measure any type of despacing or any type of strain based on this 2 theta measurement in EBSD patterns. Although physically the information should be there. It's just experimentally, it's very hard to bring that out. Yes, please.
How do we measure the 2 theta? Because we are measuring the length.
So you're asking how to measure this angle, beta?
Means the 2 theta, if you want to know the plane, which plane it is, so we have to, like we do in PM, like we know the camera length, and then we know the width, and from there we calculate 2 theta. Here, how do we do that? We don't have camera length here.
Right, so the question is how do we actually measure this beta angle? And we don't know what band is. We're going to know what it is. I'm going to show you how to do that. But assuming we don't know that, we know the pattern center. We know the specimen to screen distance because that's something that's been calibrated in, right? So for giving working distance, we know the pattern center, we know the specimen to screen distance. So if we measure this length, we can determine the angle in the bottom. And if we measure the length to the other side, we can measure the full angle, and the difference is going to be beta.
Means that length is known, specimen to detector length is known, and it's specific for
Right.
machines.
It's specific for a given working distance and a given detector position. Okay, so that is the calibration that I talked about to determine where that pattern center position is. So you know that in X, you know it in Y, and you know it in Z, which is specimen to screen.
That is fixed for a specific machine.
That is fixed for a specific working distance and detector position on a specific machine. Yes. Okay. So if you change a different working distance, you have a different pattern center, your specimen to screen distance is different. We calibrate all that in, and there's actually little equations that we can do to say if I move from 15 millimeters working distance to 14 millimeters working distance, this is how everything changes. It's all linear in the way it changes, so it's easy to calculate.
So I have to see the machine manual, what is to check what is the working and distance between, right?
Right, or calculate it. Or calculate it based on where it shows you the pattern center is. Okay. Okay, so we've said that if we know the angle between the planes and we know 3 different planes or 3 different bands, then we can do a voting procedure and determine what the solution should be. But we haven't said how to do those angles. All we said was the angle we see in the phosphor screen between 2 different bands is not the correct angle. So assuming we know this pattern center position, so coming from the pattern center, normal to the specimen, we find the specimen beam interaction volume point. So that's very much a point compared to the scale of the phosphor screen, right? So this is 30 millimeters or something, and the dot for the specimen beam interaction volume is 10 nanometers, something on that order, right? So we come from that spot, we say that's an origin. Let's put our origin there, let's say. We can measure on the phosphor screen in coordinates of X and Y that we fix to the phosphor screen. We can measure a Q and a P position. And then we can take a vector OQ and a vector OP, take the cross product of those, we'll get an orthogonal vector to the plane. So N1 will be a normal to this first plane defined by the band QP. Okay, so I've just taken this cross product and then normalized it, so it's a normalized unit vector. I know this position, right? I know where that is in this XYZ coordinate frame of the phosphor. So that way I know exactly this plane, And the plane, remember, is a geometric projection of a diffracting plane. Right? So this, maybe it's a 110 plane, something like that. It's going to be pointing straight out from where the 110 is, where that beam hits the specimen there. Okay, now we go to another Kikuchi band. We'll put an R and an S point on that. And we'll do the same thing. And we'll say N2 is the same thing. It'll be O, oops. I don't know how to erase. OP. Cross, what did I say? No, it's going to be OR, sorry. Cross OS. And those are the vectors, right? Okay, so that's going to be what N2 is. And again, it's a unit normal. Right? So now I have a vector that defines the unit normal of this plane defined by OPQ. And I have a unit vector that defines the OSR plane. Those are two different diffracting planes. So then the angle between those is just given by the dot product. Right, I have two vectors that show the normalist of planes. The angle between those planes is the dot product of their normals. Right? And of course it's normalized again, so although we've already normalized it, so we probably didn't have to do that there. Okay, so that's how we get the angle between planes. So remember yesterday we were going through the lookup tables and we were saying here's an angle of 35.1 degrees and we've measured 33, and so how does it fit in this scheme? This is how we measure the angles. Right? We know the calibration, so we know where the pattern center is. So this is just a geometry problem that we've set up based on coordinates that we affix to the phosphor screen. Okay, everybody seems clear on that. Good. I don't see any fogged over looks. All right, so now we want to determine the crystal lattice orientation. And I hope I get fogged over looks from this one, okay? Because this one isn't as straightforward. We do a little bit of bookkeeping to figure out what it is, but still it's just linear algebra. We're just transforming orientations, right? So we define a orthonormal coordinate frame looking at N1. Okay, so that's N1, so that's the normal to one of the planes we've measured. And we're going to say that's E hat 1 of the phosphor coordinate frame. And then we define a second one, and we're doing that by taking the cross product of two planes. So N1 cross N2, that is going to be normal to E1, right? Because E1 is N1. So E2 is normal to both of these. So we define an E2 arbitrarily by taking the vector we've assigned N1 to, crossing it by another angle, another normal to a plane. We have that. And then the third vector, the third orthonormal vector that is affixed to the phosphor screen, we just take the cross product of these two, right? So then we have E1, E2, E3 in the phosphor screen coordinate frame, and it is a orthonormal frame that is defined in the coordinates of the phosphor, but it's defined using bands that we know the crystallography for. Okay? So we've already measured the angles and we said, okay, that's a 110 band, that's a 111 band, and that's a 311 band. So now we take our knowledge of the crystallography that we've measured and we use HKL and we say we're going to do this C star. So this is the crystal orientation frame, but we're putting this star here to say it's not the frame that's lined up with the basis vectors of the crystal. It's actually the coordinate frame that's lined up exactly with E1P, E2P, and E3P. Right? This is just done in phosphor coordinates. And this is done in crystal coordinates. But they represent physically the exact same coordinate frame. Even though I've chosen it arbitrarily, right? I've just said here's one of my bands in the pattern, so I'm calling that N1. Cross it with another one. Okay, so these E1, E2, E3 are exactly the same as E1 C star, E2 C star, E3 C star. N2 can be anything you want, any normal to a plane that you've measured. And so can N1. You can choose anything for N1. Mm-hmm. Okay. The third one. Well, the coordinate frame we come up with, we can go through this again. The coordinate frame we come up with, we select N1 to be E1. To get E2, we cross N1 by another plane normal that we've measured. So we'll call that E2. And it doesn't matter what N2 is. It could be any of the other ones. It can't be N1 again, but it could be any of the others. Then we get a mutually orthogonal vector, so we know E2 and E1 are orthogonal to each other. And we've normalized them, of course, so everything's in unit vectors. And then E3, we just cross the other two, so that's going to be the third one that's normal to the others. So then we have a right-handed frame, E1, E2, E3, that we've defined somewhat arbitrarily, but it's not completely arbitrarily because we know the crystallography of the bands that we've used. So then we can go in and say the first C star vector, basis vector, will just be defined by this pole HKL. Remember, the pole is normal to a plane, which is what we've measured, which was what we've used. Right? So we're using that HKL pole and saying that's going to be E1 C star. Okay, so these two are equivalent. That's the important thing. They're different mathematically because you've represented them in different coordinate frames. We've done this one in the frame of the phosphor, this one in the frame of the crystal. Right? So we've defined this one in 010 and 010 and 001 that we've attached to the crystal. And this one we've just done according to the XYZ coordinate frame we've attached to the phosphor. But they're the same. So now we have something that we've measured in real space that tells us something about the crystal. It represents the same thing as what the crystal, what we get from the crystal. All right, so from there, this is actually where the work comes in, but from there it's quite simple. We have a coordinate frame, this one that we've defined up here. We have this one that we've defined here. We have the basis vectors of the crystal, that's 01, 100, 010, and 001. Right? So this is whatever you've attached to the crystal. So if it's not a cubic crystal frame, then that's going to be a little bit different, right? But if it's cubic, it's just 100, 010, and 001. So this would be an identity. So that makes it easy. So this is what we don't have. What is attached to the specimen and how it relates to the phosphor coordinate frame. Okay? So we have, let me see what I put next, just a blank one. Let's do it here. So typically we have a coordinate frame that we attach to this. Okay, so that's the coordinate frame of your specimen, right? So we've talked about that pretty much every lecture. We've said this is how we're lining the coordinate frame up. And it can be anything, right? That's also arbitrary, but that's how we typically will line that up. And then we have this one of the phosphor screen, where this is an X star and a Y star and a Z star coming out like this. And so then we know where this is. We've calibrated, so we know where that point is. So we know all of that stuff. But then we say, how do we transform this coordinate frame into this coordinate frame? Right, what's the transformation for that? So then you can determine that. And the x here, the way it's lined up, I've not drawn it very well, but the way that x is lined up, it's going to be lined up with this E hat 2, right? So it's basically going to be rotated. You're rotating your specimen coordinate frame to your phosphor. So if you're coming in horizontal with your phosphor screen like this, and you're tilted your specimen 20 degrees, then it'll be a 20-degree rotation and then flipping around the axes, right? So you do a 20-degree rotation and then maybe a couple of 90-degree rotations to get to where you want to be. Or you can just figure out what the single rotation is to get you there. Okay, so again, this is just coordinates transforming coordinates. And I just want this one to line up with this one, and that's what's happening with this calculation. Okay, so we're calculating that. So we put that specimen in there, how it rotates to that. We get this. We have how the crystal frame that is newly defined attaches onto the crystal. So now we have the newly defined crystal frame in terms of the phosphor. We have the newly defined crystal frame in terms of the specimen. In terms of the crystal is what I meant to say over here. And in terms of the specimen. And so then we just take the product of that. Just rotate them into each other. And the way that I have written this gives the orientation in the passive formulation. So remember the passive formulation, or rotating the specimen coordinate frame into the crystal coordinate frame. If we switch the order of multiplication here, it becomes the active coordinate frame. They're just inverse of each other. Okay, so this is a good point to stop. This is kind of tells you, I've told you about all the easy things yesterday, about the lookup table and those kind of things, and then this tells you actually how the bands translate into angles and how those translate into an orientation. Any questions off the top before we move on? Okay. Okay. So this is something that as soon as you start working on it, then you have questions. Right? So I encourage you to take a minute to try and actually solve one of these by hand. If you're using a lot of EBSD, I think it's good practice to see exactly what's going on. But I'm going to move on then and talk about what's been happening in the last decade or so. So this kind of indexing we've done since it first was developed, since EBSD was first developed. It's how they solved the orientations in the 1920s when Kikuchi saw it, right? He would do this kind of analysis. Okay, so now we're going to go into dictionary indexing and spherical indexing. That's what we call them. But first I'll introduce this topic of NPAR, which I think some of you have mentioned to me already, so maybe you know this already. And this is just a way to try and get higher quality EBSD patterns. So it's a neighbor pattern averaging and re-indexing. That's what NPAR stands for. And so what you do is you take these, each of these patterns indicates a pattern from a given measurement point in EBSD. So we're stepping along a hexagonal grid and we're measuring the EBSD pattern in each of these positions. And then we go back and we say, well, this one, I want to get a better quality pattern from that. So you take this pattern as well as all of its neighbors, you average them all together, and it gives you this type of pattern. So this pattern then is the average of all of these put together, right? It's just like a kernel smoothing algorithm. So you take that, you include those, you get a new one. There's a button called NLPAR, non-local pattern averaging and reindexing, where you can go out to second near neighbors, third near neighbors. You can go out and increase the size of your kernel. Now, like anything, this is a smoothing algorithm, right? It effectively smooths your data. And so if you have different patterns here, all of a sudden they'll start to blur into each other. So you have to be careful as you're doing that, right? It's basically just low pass filter that you're running across your EBSD patterns. But in a case like this, where these are all effectively the same orientation, you know, some of these patterns, this one up here in the upper left and over here on the left side, not very good quality. And, you know, you get a better quality pattern out of these. So you get higher confidence as you index it and a higher image quality. Okay, so this is just a computer exercise that I'm going to show you. So you take a EBSD pattern, and this is just artificial noise. So just taking the pattern, added a bunch of noise to it artificially. Said, okay, here's the EBSD pattern. This is a good quality one. This one over here doesn't look great. So we've artificially put the noise in. So then we look at a measure that we haven't talked about, but a measure that is the geometrically necessary dislocation density that you can measure using EBSD patterns. And this shows you if you change the step size, you get GND that will decrease as a function of step size. Increases with smaller step size because the step is in the denominator. So as you have noise in your signal, you have an inherent uncertainty in your orientation measurement. So you effectively have the change in orientation divided by the change in distance that gives you the GND content. So as the step size gets smaller, you automatically get an increased GND content. If we have a bunch of noise in the data, it doesn't matter too much when we have larger step sizes, but as we get smaller, then it becomes an issue. Okay, so we just look at the number fraction of different density determinations, and the solid line is the one that's as scanned. If we have a bunch of noise in the data, that gets shifted over. Now, why does that happen? It happens because you have a higher uncertainty in what the orientation measure is. You can't find the bands as well or precisely, right? So you get more of an uncertainty in your actual orientation. So the more noise you have, the more uncertainty you have in some of these measures that you want to actually use in your analysis of your material. And then you put all this smoothing in, and so I've just showed raw data. So these are GND, these are not GND density maps, these are CAM maps. So this is kernel average misorientation maps, and there's the scale, 0 to 5 degrees. There's the raw data. Here's what the NPAR data will give you. Smooths it down a little bit, but better quality data, so maybe this is going to be useful. Kuwahara filter, this is something that John Humphreys published in the late 90s, around 2000 or so, saying you can smooth the EBSD data using this. And then there's a bilateral filter that we've played with to look at. So each of the filters gives a little bit different information. Truth becomes subjective at this point when you're smoothing already. In general, the NPAR data is just trying to get a better quality EBSD pattern. So I tend to trust this one reasonably. This one is taking the orientations and actually running a filter over the orientation measurements. And the bilateral, so both the Kuwahara and the bilateral filter are just, it's like taking an image and blurring it down a little bit, right? So NPAR is one way to smooth out the data without kind of artificially adding this smoothing effect that blurs all the images. But it still blurs because you have boundaries and you'll introduce noise in some patterns. Okay, so this is just another quantitative result of what's happening, and you can see the original data with the black line, and the NPAR is pretty close to that. Kuaharta doesn't do too bad. It tightens things up a little more, so that's just a study to see what gets us closest to the scan data before we introduce noise. Okay, so that was just motivation for NPAR and helping understand what NPAR is. So Mark DeGraff, this author here, faculty at Carnegie Mellon University, so he basically adopted a technique that was used for TEM indexing of spot patterns that Edgar Rao came up with. Edgar Rao at Grenoble in France. He came up with this technique, and then Mark DeGraff and his group have adapted it to eBSD. The philosophy of dictionary indexing is pretty simple. You find a pattern for a given crystal structure. You create what we call a master pattern from that known crystal structure. And then you look at what your calibration values are, and you can say for a orientation of Euler angles 0, 0, 0, this is what the pattern will look like. For angles of 0, 0, 5 degrees, this is what the pattern will look like. 0, 0, 10 degrees, this is what the pattern. 0, 5, 10, right? So you create an entire matrix, an entire library, we call them, of patterns. So what's the pattern for this orientation? What's the pattern for this orientation? So we create an entire library. It takes about, depending on your computer speed, 10 to 15 minutes to create a library that has patterns that are 5 degrees apart. Okay. Now, usually we want to index better than that, so we'll go down to 2 degrees or 1 degree, something like that. But the philosophy is you have all these patterns that you've stored. These are the master patterns. You take your experimental pattern, you do a cross correlation with each of the stored patterns and say, okay, that one's best. That's the one we're going to use. We get it? We haven't looked for Kikuchi bands. We haven't measured interplanar angles. Right? We still have to know the calibration. Still have to know the calibration becomes even more important with dictionary indexing. All we're doing is saying, this has a bright point. Is there a bright point in the same position as in the index pattern? Right? Here's some bright positions. Are they the same bright positions in the dictionary pattern? Right, so we create this library of patterns that has specific number of degrees between each one of them. We match it up, say that's the one that matches best, and then we assign the orientation to that. We can do the same thing with phase identification. Right? Set up the library of patterns. Say here's 3 different possible phases. Match them all up together. This orientation of this phase matches best. Really brute force, right? It's a really brute force technique. So when I first saw that they had adapted it to eBSD, I wasn't very impressed. I thought, wow, you know, we do pretty good with eBSD with finding Huff bands and things. So why would I ever use this? All right, so here's ways, and there's a lot of software online for this. There's a package called EM Sphinx on GitHub. EM Sphinx. I think it's like that. Anyway, you can go to GitHub and look at dictionary indexing. You'll find software that will simulate patterns, create a master pattern, do all these. All right, so to build your dictionary, you put in your crystal structure, all the atom positions, everything you need to know. You need to know what the SEM accelerating voltage is, right? right? Because you have different width bands. If you start getting different, you have to know all the geometry, all your calibration information. All those things will slightly change the position of your pattern, which will completely mess up your dictionary indexing. Okay? You know that. You can apply that to the orientation space, so you discretize all of it, and then you have all your patterns that you can put out. All right, so if we look at pattern simulation, this is an experimental pattern. This is a kinematic simulation. So if any of you play with TEM much, then you'll know there's a difference in your kinematic diffraction versus your dynamic diffraction. So kinematic diffraction is much simpler. This pattern pretty much looks like what you get in your experimental pattern as far as bright regions being bright and the bands being seen here. So it's not a terrible way to do it. If you do a dynamic diffraction, you don't know where all the electrons are going, right? You get multiple scattering events. You don't know what's exactly happening. So you do a standard backscatter electron Monte Carlo type of simulation. You put in all of the possible energies, what the depth is, exit directions coming out, all this kind of stuff. I won't go over all these things. Let me see if there's anything else. Basically just, you know, tilting of your specimen, so you have to know these kind of things. And then you get a pattern that looks like this one, right? That pattern looks pretty good. It looks pretty like an experimental pattern, right? So the calculation's a lot more involved, but all of a sudden we have patterns that look like our experimental patterns. So now when we do a cross correlation, we can determine pretty nicely which is which. It's not exact, right? It's a Monte Carlo simulation based approach. So you have atoms going all over the place, but in a statistical average, right? In the what we say is ergodic hypothesis, the ergodicity of the diffraction, meaning that locally your electrons might go all kinds of different places, but globally you're going to get the same behavior, right? It's ergodicity. So we have that. So this is one that's shown at 2 keV. This is one shown at 6 keV, and one shown at 12 keV for the same specimen, which I'm looking to see if it tells me. I don't remember what this one was. But you can see the bands are different. This is mapped over a sphere, so that's why it looks like it's mapped over a sphere, right? Now you're comparing against patterns that are seen on flat surfaces, so you have to map that down to get your library of patterns. But using physics, you get a really nice simulated pattern. Takes a little more computational time, but once you've calculated the master pattern, you can just store it and use it anytime you do dictionary or spherical indexing of that type of material, right? So in the newest software that's coming out where you can do these kind of simulations, a lot of times these patterns are stored. If they're not stored, you can put in all the information that was on the previous slide and calculate a pattern. These are computationally intensive. It's computationally intensive to do the comparing and the cross-correlation between the patterns. So you do need stronger computers. I was thinking of showing you this kind of indexing on my laptop, but I don't have GPU in my laptop, so I could get a laptop with a GPU, but I just don't. So I can't show you how it works from a software point of view, but we can show what the results we get. Okay. All right, so dynamical simulation of the patterns is pretty much what everybody uses. Okay, that's what we're using for dictionary indexing or spherical indexing. And it's a little daunting, all these equations, but the codes are available, so that's nice. So there's the scattering, there's the position specifically. You get this spherical pattern. and then you map it onto a flat plane that has your geometry and your calibration all included with it. All right. So here then is showing your specimen pull piece where the detector is. This is what the pattern should look like. If we look at a sphere, that is taking this part of the pattern, mapping it into the space that we look at on the phosphor screen. Okay. So this is a sphere that's been kind of unfolded and flattened out. All right, so that's what we're looking at is these positions.
Why only part of the why this black region only we are seeing?
So we've simulated the entire pattern as a sphere, right? Because we think of diffraction and coming out a specific angle or a specific distance. So we simulate it as a sphere, but now we're looking at patterns on a flat plane. And so we have to project that sphere onto the flat plane. And this is the shape of the region we would see in this square. Right. Right, so that square, that side would be this, that side would be here, this side up here would be that, and this big curved side would be this side. Right? Yeah, it's a distortion, yeah. From making the sphere flat, right? Okay, so it's rotated, put into position, and then we do that every 2 degrees, every 5 degrees, whatever, for dictionary indexing. Okay, so this is just showing a little more about the dynamic simulation. And again, it was done over a sphere for a given crystal structure. So an FCC crystal structure, it was done over a sphere, flattened out, and then compared with the patterns that we measured, right? So that's the process. And I've shown a lot of the papers down here that they've used. So then we look at the patterns and we say, there's our experimental pattern, here's our simulated pattern. For the same geometry, the same beam conditions. This one is a little bit brighter down here than this, right? But as far as the features in there, they're all pretty similar to what we see in the experimental pattern. All right, so then we have our master pattern, what we call the master pattern. We put it for all orientations, and then we do the sampling of orientation space, right? So we divide orientation space into bins. Now we call it a cubochoric sampling because if we just say here's 2 degrees, 2 degrees, 2 degrees, something like that, then the space is really nonlinear, right? So one space is going to have a different volume of orientations that's included than another space. So sometimes we take that into account as well, that we will separate orientation space into specific types of bins that are maybe uniform volumes. So we calculate those, that orientation space, everything is stored in files. So this is again talking about sampling orientation space. So we have to give a specific misorientation angle between the sampling points. That's something we have to come up with. Do we want 5 degrees, or do we want 1 degree, or do we want a half a degree? And the only penalty we pay is in calculation time, right? Memory and calculation time. Because you have to create these simulated patterns for each individual one of those that we do. So here's an example. Here's Rodriguez space. Going 5 degrees through Rodriguez space. So these are 2 positions or 5 degrees from each other, and all these dots in here 5 degrees from each other. Here's a sampling that's 2.5 degrees. Right? So you know, since we have a 3-dimensional space as we cut that down by half, right? If we cut the angle down by half, then all of a sudden we have 8 times as many points, right? 2 cubed more points. All right, so here is an example. Here's a really nicely indexed EBSD image using Huff indexing. We have a 2.5 degree dictionary indexing and a 5 degree dictionary indexing. All right, works reasonably well. All of a sudden we start seeing features in this one that we didn't see in this one. And the reason is because we can have a nice smooth transition across a grain from different orientations, right? If it's misoriented by a 1/4 degree or a 1/2 degree, we capture that. And in here we don't capture it because we only capture 2.5 degrees, right? So then we get these blocky features look like 2.5 degree subgrains inside our grain. And then 5 degrees just misses a lot of them. It can't do the cross correlation good enough at 5 degrees. And that's for high quality patterns. Okay, so here's patterns that we're looking at. And these patterns, it's all showing the same data. So what they have done is introduce noise into the patterns. So that's the raw pattern, progressively introduce noise into the patterns. And then do the EBSD data, just calculate it based on the patterns that are coming in. So these in the left column, these are from Huff indexing, and you can see when the patterns start getting bad, we start getting speckle in here and continues to get worse. So we end up getting basically no data here at the bottom. If we use a dictionary approach, again, looks pretty good. As we continue through here, even when we completely lose all the data from Huff, we still get almost reasonable looking data from dictionary indexing, right? So we can't pick bands out of this very well, but there's enough features in here. You can kind of see lines and points. There's enough features that we can cross correlate it almost reasonably and get good data from the dictionary indexing method, right? All right, pros and cons. So more robust, we've shown that you can get more good data points than you can when using Huff for poor quality patterns. It's way slower. Typically, we don't do it online. Typically, what we do is we save patterns. We save our individual patterns for every scan. Gets to be a lot, right? Sometimes it's hundreds of thousands of patterns. So those files get big quick, saving hundreds of thousands of patterns. We save them in a small format, but we still save a lot of patterns, right? So we're typically, and when we do dictionary, we're not doing it online. If you want good resolution, you need really large dictionaries, and then you're still not getting as good angular resolution as you would with Huff. And then there's, figuring out how to do it for your specimen takes some time. So I spent about 30 years telling everybody, don't save your EBSD patterns. It's not worth it to save all your EBSD patterns, because you save the Huff parameters and you can go back and use that and re-index with a different phase if you need to, or whatever you need to do. Now that I use dictionary indexing and spherical indexing that we're going to talk about next, and I use high resolution EBSD where I'm comparing patterns, now I tell everybody save all your patterns. So I've completely switched from what I did for 30 years. Now I've completely switched and say save all your patterns all the time. Memory's cheap, right? Ish. You can buy an external 1 or 2 terabyte drive. You can save a lot of data on there. Okay. All right.
How much time take for this dictionary indexing dictionary?
So in the systems I have, again, it depends on exactly what systems you're using. The question was, how long does it take to do dictionary indexing? So on this one, after we have all the patterns collected, we have the master pattern that is simulated, and we have the dictionary created, which takes about 15 or 20 minutes to do all that. It would take, for 200,000 points, it would take probably another half an hour to do the analysis and get the map out for that. So it's not like 3 weeks or something, but it's not like sitting there and seeing the data come out immediately like you do on your fast EBSD scans. You know, you can do a few 100,000 points in a few minutes these days with Huff indexing.
So it may sound silly, but how do you specifically compare the exact same experimental data with the simulated data?
Yeah, so the question is, how do you compare the exact simulated data with the pattern that you have? So you don't know what the pattern you have is going to be, but after you've created your master pattern and you have this spherical pattern, then you can take 2 degrees at a time or 1 degree at a time, whatever you want to put in your library, create those so they would look exactly like your pattern, store those files in this dictionary, right? And then you take pattern to pattern and you run a cross-correlation algorithm. So it's all cross-correlation algorithms that are comparing those and then saying this correlates better than that. And you get a very nice number that says this is the best comparison. But you're doing that for all your patterns, so it takes a long time. Okay. Okay, and of course, this is just showing what your dictionary size is going to be, how many patterns you would have to store for different angular resolutions for the different crystal symmetries, right? So for cubic crystal symmetries, it still gets really big once you get down to about a half a degree or so. If you look at it here, half a degree is that much, 10 million? What's that, 1 crore? Is that what we say, 1 crore? Okay. Since I don't use that other than when I'm in India, lakhs and crores. So I say 10 million, you say 10 crore. Okay, good. 1 crore. All right, so this is just, this is answering your question about what exactly is done. So this is looking at a piece of this lighthouse image. You're cutting it into a bunch of different boxes, and then you're correlating and you're saying, here's the image that I've actually have, which box does it belong to, and you can go in and correlate it to what that box is, right? Just the cross-correlation algorithm. So this is what it's doing. Here's the cross-correlation, runs it on all of them, and it will identify what the best one is. And you can run this with FFT, so it can run reasonably fast-ish. Okay. Any other questions for dictionary? This is now I'm going to go into spherical indexing, which is pretty much exactly the same as dictionary indexing, but it's a lot faster. A lot faster. This guy named Will Lentha, who was one of DeGraff's students. People amaze me how smart they are sometimes, but able to do spherical harmonic, use spherical harmonic functions, which we use in texture analysis all the time, and able to completely speed up a pattern, or completely speed up the indexing, the comparisons, not even create a dictionary of patterns. All you need to do is create a master pattern. And then we can do it. We can take that half hour of indexing time for 200,000 points and knock it down to a minute or less, right? So it's much faster. Anyway, so here's what it started as. Can we do cross-correlation on a sphere? Can we just, instead of creating all these individual patterns, flattening them out, can we do it on a sphere itself? So here's our master pattern. Here's what we get from our detector. And can we say, okay, yep, that point is this one, so we can correlate that down into that, right? Then all of a sudden it'd be a lot faster. Then from there we could say this is what the orientation is. So we don't have to discretize now into 1 degree bins or 5 degree bins. We just have to do the correlation over the sphere, which means this pattern has to be represented on a sphere, even though we don't collect it on a sphere. See? All right. So how are we going to do that? Let's move on to this. This is the spherical harmonics. Just quick, we are gonna come back to spherical harmonics because we use them as basis functions for texture analysis. But these are now surface harmonics. Right? So these are two-dimensional spherical harmonics. And for the spherical harmonic, we have two angles as arguments, a theta and a phi here. Right? And then we're just saying we're running a transform over this theta and phi space, integrating over all that space, and it's going to give us some kind of a function that we can use to correlate with our images. All right, the basis function, the definition of the spherical harmonic, the surface harmonic function is this one. So this y function is a surface harmonic defined over the angles theta and phi. L and M are indices, right? Because these are harmonic functions, so you get a first order, second order, third order harmonics. So as these increase, you get increasing complexity. So you have kind of an average, so it's just a sphere, and then you get one like this, one pointing this way, and then you get increasing complexity of what the actual functions are representing, what kind of information they have in themselves. But you can think of it with my simple brain. Dr. Masarovich would not be happy, so don't tell him that what we're doing here. But in my simple brain, I think of it as a cosine function or a sine function. I put in a value of an angle. I know what the value is, right? It's just a function. I put a function in my sine, right? So I have a sine function. I put in 20 degrees. I know what the sine of 20 degrees is, right? But now we're doing this with harmonics, so it's like taking your sines and cosines in a Fourier series expansion or harmonic expansion, or e to the I pi something, right, which we can represent as sine theta plus I, right, cos theta plus I sine theta, I sine plus whatever it is, okay? And then you can have different harmonics based on that. So you can do the same with sines and cosines. But spherical harmonics, this is a complex looking function. This is just an associated Legendre polynomial here. So if you've taken differential equations or applied math, it's just a solution to a differential equation, right? So that's an associated Legendre polynomial. So everything is just numbers, right? These are integers, that's an angle, everything's just numbers. So that gives us the value. We plug in our L and our M, we plug in our theta and our phi, and we get a number for that. Okay. Okay, so then we can represent these functions based on a series expansion of those functions. Or we take the first order functions plus the second order functions plus the third order functions. And I'll describe this a little better when we're doing texture analysis, but it's the same kind of thing that's being done here. And then you do your transform. Okay. So spherical harmonics, just math, don't be scared. Then we do a cross correlation for the orientation. So again, I'm showing you all the equations. I'm not going to go through them really carefully. But what we're doing is we're taking the pattern, we're representing it with spherical harmonics. Just saying, here's the bright parts, here's the dark parts. And now we're taking that and we're doing a cross correlation over the entire sphere. So we have the measured pattern, cross correlation over the entire sphere. We're saying it matches up best with that point. So there's a couple of parameters we put in here. We put a bandwidth, which is basically similar to what you would think of as a smoothing, right? How much smoothing do we want to do in our function? How much, what order of series expansion do we want to go to, right? That's basically what it's talking about. So if you go to higher bandwidth, you're looking at finer details, just like if you do a Fourier series expansion, you go to higher values, you get sharper peaks, right? If you want to look at a delta function that's a nice sharp peak, you start off with an average and then a single peak and then a bunch of them. If you go to really high order, then you'll see a nice sharp peak, right? Okay. Anyway, so you have all of these harmonics. You truncate it at some level, that's this bandwidth, and then you are able to go in and compare your individual pattern with all of the other, the master pattern. This is showing what the smoothing is doing. So if I truncate at 68 versus if I truncate at 158, and that's the raw pattern. So it looks pretty identical. This one looks blurred out, right? This one looks like it has deformation in it, basically. So you have to determine what you're going to do as far as bandwidth. You look at the grid spacing here. This is just the grid over the sphere of how fine of features you're looking at. It's not a measure of how close you can determine the orientation. So I don't want to confuse you with that, because dictionary indexing, when we showed this kind of thing, it was you get either, you know, something that's oriented at 10 degrees or at 12 degrees. So if it's 11.2, you don't get that. In spherical indexing, you do get 11.2. Okay? So this is just for the patterns themselves. Now, if we look at this spherical indexing, we look at you know, a pattern again that has noise introduced to it. Here's what Huff indexing would do, even when including NPAR. That's hiding there from us, but it's NPAR. This is the dictionary indexing solution. This is the spherical indexing solutions with different bandwidths. Right? So you can do at least as good as your dictionary indexing. Some angles are a little bit different. You can see some different shading, like in the grain right here. That shading is a little bit different than that grain shaded. But that's because we're not fixed to a set of files that's at 10 degrees and 11 degrees and 12 degrees. Now it can go 11.6. Okay. Yes, question. Yeah, I'm cheating here a little bit. So I was told that highlighting isn't visible. So if I go back to the laser pointer, then it's visible, yeah. So I was comparing this grain with this grain, right? So this one is a little bit dark or a little bit lighter than that one, so it means it's slightly different orientation, right? Which you would expect in dictionary indexing, and you would expect some blocky things to occur that maybe wouldn't occur in your spherical indexing. Okay, so I want you to know that it's similar in nature to dictionary indexing, right? Because we're comparing a master pattern and doing a cross correlation. But since we use this clever spherical harmonic formulation to look for where the peaks are, we don't have to create a library. We can just map our pattern onto the sphere and then see where it correlates best, right there in spherical space. Okay, so here's another example. This is hot rolled magnesium. There's Huff indexing. Anytime you see speckles, that's bad data, right? That's spherical indexing. Nothing was done to polish the specimen different. It's exactly the same patterns were used, but all of a sudden you have data that looks better. One of my more senior students, we've just started using this in the last year or so, the spherical indexing. And he had been struggling with his deformed specimens. And now he's using spherical, and he said, how did you ever index deformed materials before you could do spherical? It wasn't possible. I said, of course it's possible. We've been doing this for a long time. Of course we do it. But in his brain, right, all of a sudden he was having data like this, and now he gets data that looks much better. So he's happier with that. Okay. Okay. This is the same maps. It's just including image quality onto the map. Spherical indexing is including a confidence index. Confidence index now is defined very differently. This is one of the problems we have with spherical indexing right now. We don't have a nice chart that says a confidence index of 0.1 is going to be 95% accurate. Right? The confidence index basically gives a measure of the cross-correlation routine. How correlated are they? Right? Is this correlated very well, or is it not correlated as well? And it doesn't seem to work as a confidence index to tell you that you have the right solution or not. But it does tell you some really interesting things. I mean, one of the things that DeGraff has shown is that he did a map of a very clean specimen and then a specimen that had just a small amount of dislocations. And he showed that he can pick up, as he's scanning across, he can pick up exactly the positions of single dislocations, because it just interrupts the correlation just enough that you get a worse confidence index. Right? So using a confidence index map, you can see where the positions of the dislocations are. I mean, that's, to me, that's nothing I would ever expect to get from EBSD data. All right, here's a highly deformed duplex steel. Again, there's your Huff image, your spherical image, dividing it into ferrite and austenite. This is when we're trying to go faster with the Huff. Right? So nitinol specimen, nickel titanium. Almost nothing from the Huff itself. If we use NPAR, we can start pulling out a few features. If we do NPAR plus spherical, all of a sudden we have a map that we could use. Right? Shot peened aluminum surface. Here's the surface again, Huff indexing. So this shows some of the substrate, and this is just focused up here on the fine grain region. So we get some data. I have a lot of scans like this in my life, where we get something that looks pretty reasonable. The spherical is done probably in a factor of 100 times faster than the dictionary when it's actually doing the calculations. You store the patterns, you go back. This one takes a long time, this one's done immediately. Okay, here's a specimen that just has a rough surface. This is what we call orange peel, right? So it's orange peel on the surface from texture effects where you get a lot of roughening. We don't get very good data on the Huff, and that's because we get a lot of these intensity gradients on the specimen. So if the surface rotates just a degree or two, then it really messes up our background, right, from the EBSD indexing. So there's Huff plus NPAR, spherical, and spherical plus NPAR. Then this is just one that's from from a material that I have no idea what is. It's a rock. If any of you are in geology, you'll know what that word is. Maybe somebody knows anyway. Any?
There should be one student from geology.
Oh. They're not confessing that they know what it is. Anyway, that's a rock. Rutile, ceramic, right? TiO2. So these patterns, you know, it's just showing that we don't have to stick with cubics or hexagonals. We can do other types of things. You do need stronger computers. The faster the better, of course, You know, the more money you spend, the better off you are. We are right now using this one, I believe. This is our GPU card that we're using. But it works reasonably well. And this is emphasizing what happens if you're looking at orientations from a dictionary method. Right, you're looking at that point, that point, that point. With a spherical method, you're analyzing all points. Right, you're not confined to just those discrete points. You're looking and saying, where's the best fit anywhere? So this is supposed to represent an orientation space. Right? So this is Euler space, consider it 3 dimensions, whatever. Okay. And then this just shows how they're refining, and sorry about the text here, I'm gonna just skip through this. I think what I wanna do is just ask for questions, comments on this. Let me see, let me just go through the end of my slides here and make sure there's nothing that I wanna play with. There's a lot of things we can talk about, but okay. Questions, dictionary, Huff, or spherical type of indexing? What's questions you have in your head that you've been saving up?
And after the questions, we can go for small t.
Okay.
For indexing, how much pattern we require? How many patterns should be there? How many patterns should be there in the dictionary for good match?
So you calculate a master pattern, which contains the entire sphere, and then you map, for dictionary method, you create what those squares would look like, right? What does my phosphor screen pattern look like? So you take each one of those and you'll divide them into however many points. I mean, you know, we say Huff indexing has approximately a half a degree of angular resolution. Is about where we're at with Huff indexing. So plus or minus half degree in there. So if we want the same resolution as we get with Huff, we would go down to half a degree, which is a lot of patterns, right? It's 10 million patterns for cubic, and much more if you go to lower symmetries.
The
Right.
pattern means all these patterns are the region of the sphere. All these patterns are region of the sphere.
The patterns that we save in a file for dictionary indexing are regions of a sphere that have been mapped based on our calibration, our specific system calibration, you know, 20 keV, whatever we're using, and saved as 1 degree increments, 2 degree increments, something like that. Yep. And then each of our individual patterns gets compared against the entire dictionary, and then we go to the next pattern, see which one has the best cross correlation.
So only one angle is required to have the area on the sphere. We require more than one angle. Two angles.
So the question is, do we need more than one angle? And yes, we do need more than one angle, right? So a sphere, you use 2 angles to define the surface of a sphere, right? A polar and an azimuthal angle. So those 2 angles you need to define the surface all the time. Yes. So that's why when we do spherical indexing, we run functions that are based on that sphere, on those 2 angles that we call theta and phi in this case.
So why do you take only one angle?
So the question is, why do I take only one angle? And I think it's because I'm a simple person, so I think in one angle, and then I know it extrapolates to whatever dimensional space I'm working in. So that's why I think of my spherical harmonic functions as a trigonometric function, right? Because I can understand those nicely, because I've learned those since I was small. So, yeah. So sorry if I confused it by doing that, but to me it's just, so I showed the orientation space, which was these green things, and the individual dots, and orientation space is a three-dimensional space, right? So we kind of showed it in a two-dimensional grid, but that's just meaning points through orientation space.
So you need to have the phase information. You should have the phase information.
You need the phase information, you need the geometry of your system, and you need the accelerating potential. All of that is required to get a good simulated pattern. Mhm. Yes. Okay, I see no other questions. I don't know if there's online questions, but nobody has said anything, so I'm assuming not. So let's go ahead and take a break. Okay? Okay. Oh, you're live. Okay. We're live. So we should start. So maybe you could tell when I finished that I thought I was done for today, but Professor Biswas said I should talk a little bit more, so I'm going to talk a little bit more. So it gives me a chance to talk about some things I wasn't going to talk about because I skipped over some of the other slides to finish up by 10:30. So what I'm going to show you is a series of images from platinum. Now these are simulated patterns, right? These are the master patterns like I was telling you about that are calculated from dynamical consideration. And these are done at voltages from 30 keV down to 1 keV. And then we'll talk about why it might be important to go to low keV for some situations. But if you look at a 30 keV pattern as you go down in voltage, so there's 20, this is all the same pattern, right? 20 keV, 10 keV, and then start going 1 degree at a time, 9, 8. You can see how these patterns are changing. Once you start getting at some of the lower voltages, you start seeing a lot of features that you wouldn't necessarily expect otherwise, right? We see a lot of these rings. These are higher order Laue zones, Holtz lines we call them, H-O-L-Z. So these are Holtz lines, and sometimes you can use these to get a little bit better measure of D-spacing actually. So you get some of these features in the electron backscatter diffraction patterns that maybe you wouldn't get if you were working at higher voltages. And it gives a problem if we start to consider Huff indexing. Because in Huff indexing, we're looking for Kikuchi bands, right? We're looking for straight lines in the image. And as soon as we start to get to some of these lower voltages, some of these straight lines, I mean, here probably would work okay still. I have indexed 5 keV patterns before. But these bands starting to go away in favor of some of these higher order features. If we look at this one, now 4 keV, probably you can still see zone axes. You can still see where lines might be. Maybe still be able to index. Here's down to 3. The commercial systems that are available, there's now what they call a clarity detector, which is a low voltage EBSD system. And the super clarity, so the clarity is designated at 7 keV, and the super clarity is down at 3 keV. So this type of a pattern is common now that you might get in low voltage EBSD systems. So why go to low voltage? Right, that's the question. Why would we care about going to low voltage? There's a couple of answers. First one is that it reduces charging effects. Right, so if you have a specimen that's not conductive, that you need to coat to get proper information from, and the coating always gives trouble because it interferes with the electrons going in, interferes with the electrons going out. So it makes it so you don't need to coat the specimen going to lower voltages if you have non-conductive. So ceramics, geologic specimens, sometimes crystalline polymer specimens or crystalline biological type specimens, bones or teeth or some of those kind of things that you can get patterns from. A lot of people look at lobster claw shells or abalone shells, these types of things. You know, you can get nice patterns. They're just not conductive materials. So it makes it so you can actually image reasonably well without having those complications. If I'm trying Huff indexing with something like this 3 keV pattern that I'm showing you here, I wouldn't be able to index it very well. I need to go to a dictionary type of a method where I calculate the pattern and now I'm just doing cross correlation, right? So now this physics and the geometry of these lines that we looked at so carefully, and I told you how to calculate those things, these don't come into play with these types of patterns because we don't see those bands. Okay, 2 kV, 1, right? 1 kV is kind of interesting because if you look at some of these zone axes, you start to see Kikuchi lines inside the zone axes. Has anybody ever seen that before with anything? Any TEM people in the room? No, no TEM people. There's a technique called convergent beam electron diffraction that we do in the TEM, where you get patterns that are very similar to this, where you get the zone axes, the spots are getting larger, and all of a sudden you see the Kikuchi lines inside the zone axes. So this is it's pretty interesting, the physics that you can start seeing when you look down at some of these lower patterns, the lower voltage patterns. Okay. The other reason besides just charging, if we're looking at a non-conductive sample, the other reason to go to lower voltage is to decrease your interaction volume. Right, so maybe some of you have heard of TKD or transmission Kikuchi diffraction. If you do transmission Kikuchi diffraction, you're looking at a thin film, a TEM type specimen, and you don't get the teardrop shape. Mosquitoes bothering me. You don't get the teardrop shape interaction volume anymore because there's no volume down there. Now, if you go to very low accelerating voltages, all of a sudden your depth of penetration gets much smaller. So you can see there, 30 keV, we're getting signal from about 15 nanometers into the specimen. When we're down here at about 2 keV, we're getting information from only 1 or 2 nanometers into the specimen. And the same thing, this is how much width, how much the beam is spreading around where the interaction spot is. And at 30 keV, it's significant. Is up here around 70 nanometers or so. So that's the best resolution you could get working at 70 nanometers. Again, this is for these platinum specimens, for these platinum patterns I was showing you. But as you come down in accelerating potential, below about 5, it decreases to where we're now below 5 nanometers. Right, so if we can work with these types of patterns, these 1 or 2 or 3 or 4 keV type patterns, now we can really increase the spatial resolution of the information that we're getting, right? So that's the reason we would go to that. And I think the only way to do it right now is with dictionary or spherical indexing. It's the only way I can think of that would be reasonable. Other than that, we would have to come up with different routines to pull out the different features that we're seeing, since it's not the bands anymore that we see. Okay. Okay, so I think we have a few minutes left, but I don't have anything else I want to say, unless we go back and cover some of the stuff I skipped before, because I was trying to finish by 10:30. We should communicate first next time. Anybody low voltage EBSD questions? Anybody, any thoughts or any doubts, let's say? Yes?
Where we can get the database?
From where do you get the database? Of those patterns, you mean?
Yes. Dictionary indexing, we have to match cross-correlate with the database.
Right.
For different crystal structures, from where we can get.
Right. So there's tools available online. There's tools available in GitHub if you want to do the dynamical simulation of the EBSD patterns. The other thing is, if you have, for EBSD, if you have OIM analysis, OIM analysis 9, they've started including those tools in OIM analysis. So you can go in and use OIM analysis 9 and simulate a master pattern. And they have some of the libraries of the patterns already stored. So, new thing that's been happening in EBSD. So,
So you mentioned EMS links.
yeah,
That is an open source software, open source license software. That is for this
Yeah,
simulation.
that's open source. And so it will, you can go to GitHub and download that.
So that will carry on with this dictionary indexing or this dynamic simulation? Like sorry, spherical simulation. Which one?
So they use the same master pattern. So the simulation is the same.
Okay, so but I can generate my master pattern with just the lattice whatever crystal structure that I'm using. I just need to get the input and then I get my master pattern.
Right. Right. And you can do a kinematic simulation of a pattern quite simply, right? So you just calculate where your diffraction bands are and you know put the relative intensities. And so the kinematic one you can do quite simply, but the dynamic one that actually looks like a real EBSD pattern, that takes a little more effort. But there's a lot of publications and there's a lot of software that's available for that. Yeah.
And correlation can be also done there in software. EMS mix.
The cross correlation.
Cross correlation.
So the entire dictionary indexing is available. I think there's 3 different codes that you have to run. But you can download that, and it's pretty good help file, and there's a lot of people who've been doing it, so there's a community that's been using it. So there is that's been going on for about 3 or 4 years now, 5 years maybe, from open source. And it's just been the last year or so that it's been incorporated into some commercial software. Okay. Yes?
So can we calculate the anisotropy property from EBSD data?
So the anisotropy properties are from, depending on what type of properties, you will actually determine those from some other types of measurements. Now, once you have a polycrystal, if you know what the properties are in the 100 direction and in the 111 direction and the 211 direction, all these, the different anisotropic properties that you know from some other technique, right? Maybe it's superconductivity, maybe it's strength, maybe it's, whatever that you're looking at. Then you can input that data. Elasticity is another one, stiffness. But then you can use the data from EBSD to determine what the global properties of your material is going to be. Okay, so you can measure the texture. So say I have a lot of 111s, and so I'm going to have a poor superconducting critical current is not going to be adequate for that specimen, and so you need to have all 001 lattice for that something.
Which software we can
So this is information that you get from all over the place, and so if you were looking for elastic constants, a lot of those are tabulated in even textbooks now. That you would get, what are the elastic constants as a function of direction for different materials. So you could put those in, and if you want to check out what the elastic properties of your overall material are based on your EBSD data, it will ask you for those tensor components. And so you can go into OIM analysis, you can input those tensor components, and then calculate what the properties are. Because you know all these orientations, right? And so all this that Professor Masarovich is showing us, and you'll be able to, from the stuff he's showing us, you can model the anisotropy of the different properties, right? So you'll say, okay, this is what it shows from the model, what the different properties are. And then from EBSD, you measure the material and you say, this is what my distribution of orientations are. Then you can take his models along with your data and say, this is what the properties of my specific specimen is going to be. Okay. So EBSD data doesn't give you the fundamental properties. It just gives you the rotations, the orientations of the lattice and the phases. And then you can take what you know about anisotropy of each of the phases and determine global properties of your material from EBSD. Okay. Any others? Yes.
Can we do this if I have a brittle kind of failure, so I have cleavage facets. So is it possible to do indexing on that based on this dictionary indexing and spherical indexing?
Sometimes, yeah.
Because in half best it is means there are lots of noise in that.
Right. So a lot of times the problem with cleavage is you have different orientations of your surface, right? You have little steps and things on your surface, and that's where you get all the noise. And sometimes you can do better with Huff indexing, and sometimes you can do better with, or not better with Huff, better with spherical or dictionary indexing. And sometimes you can do better using a background strategy called a dynamic background correction. Maybe you've seen that, but it doesn't try and average an entire background from a smooth surface first. It takes each pattern, smooths it out, subtracts that smoothed out from your pattern, and sometimes you can get pretty good data just with that. So I would try that if you don't have access to dictionary right now. Yep. Okay, any others?
I think in chat box
Oh, okay. So there was a question in the chat, but I don't see it here.
Chat is not there, sir.
Oh,
No
but I
questions.
see somebody.
That is the number of participants.
okay. Never mind. Never mind, as you were.
Yeah, somebody raised my hand.
Okay, well, I'm assuming there are no more questions, and so I am going to yield the floor to Sanisha. Please.
Thank you, sir.
I'm 1 minute late,
Shame on
so I owe you 1 more minute.
you. You'll do better next time. Well, you owe me.
I owe you lots of minutes. I tried to give it to you, but I was denied.
Okay, it should duplicate the display now. Can I have a display? Oh, full screen. Yeah. Yeah.
Yes.
Okay. So, what I will try to do today is do first a little short review of what we have done. And for that, I'll need to first go to my old notes from the first lecture. The purpose of all this is to model evolutions of microstructures using a phase field model, phase field formulation, and finite element method. None of which we have touched yet. Right. So we are still working on a background. And I showed you some kinds of problems where we need mesoscale models, where we need to use phase field. The problem, of course, is phase field is a continuum theory. So we need to cover continuum mechanics. And in the last 2 days, I have dumped upon you approximately 3/4 of a graduate course in a continuum mechanics, 3/4 of a semester. So if you are shocked, I would not be surprised, right? It's hard and it's a lot. But we need that background to start with phase field models. And we have, we still have plenty of time. We will get there. But first we need to understand the basics. Because we are dealing with, well, three-dimensional problems where multiple physical mechanisms may operate. So we have stresses and strains, so we have elasticity and plasticity. We have diffusion, we have lattice growth. We may have phase transformations. So all that needs to be put into mathematical context, and that mathematical context is continuum mechanics. So in our discussion of continuum mechanics, we have briefly discussed the basic. What is continuum? How does a material point move, and what is material point? And we discovered there are two types of material points. One is attached to mass, right? Not atoms, mass. The other one to lattice. Again, not mass, and again, not atoms, right? Not individual atoms. So from those first elements, there follows the concept of material field and material derivative. That is a time derivative following our material point, which is different from a partial derivative with respect to time. And there follows transport theorem. That is, if I have a moving volume and I have a quantity inside that volume which is given either per unit mass or later on we have seen per unit lattice height, I can easily find a rate of change of that integral by integrating material derivative of that quantity inside that volume. So, well, we covered lattice continuum diffusion mechanisms. We had a discussion first on the meaning of reference configuration. So in our continuum theories, we say some reference position, capital X, is mapped during time t into current position x. So this one turned out to have this current we have, right? in this instant of time, my point is somewhere, right? Where that point was, that material point, that's an open question, and this capital X will usually have mathematical meaning in a sense that it is not attached to particular atoms. Only in solids without diffusion. Question?
F is used to transport.
Is there a similar quantity which define the mass transport? Good question. Excellent question. Yes, it's the same quantity. See, F follows, F is, let's see, this is my F. But the difference in mass and lattice continuum is in defining what is this X. Well, capital X. So as capital X goes to small x, well, in mass continuum, it's a piece of mass that moves. In lattice continuum, it's lattice sides that move. So the definition of F is fundamentally different, but formally, mathematically, is the same. Once you decide what your material is, you use the same. So the answer to your question is yes, it's F. It is the same tensor field. It just has different meaning, but mathematical formalism is the same. So only in solids without diffusion. Where is my cursor? Here it is. Only in solids without diffusion I can claim that I'm following a bunch of atoms, well, during deformation, from capital X to small x. Okay, so then we did a little bit of kinematics. We defined our fundamental quantity. Now this has nothing to do with our original choice of what material is, right? F works anyway. Capital X goes to small x, and everything I need to know about deformation is hidden in this tensor field, and I should perhaps emphasize it's a rank 2 tensor, and it is we think of it as a function of capital X and time. So it transforms an element from reference configuration into current configuration. So small element dx here will be transformed into small element here. Now, then we discussed polar decomposition or multiplicative decomposition theorem. We can decompose this deformation gradient field into deformation and rotation. Well, we discussed properties. And we can do it in two sequences: first deformation, then rotation, or first rotation, then deformation. The thing with deformation is it only stretches principal fibers, but fibers which are not principal, like this green one, will also get some rotation and stretching. But rotation is pure rigid body rotation. This is this tensor R. In terms of principal directions of U and V, these tensors can be represented in this way. And the thing that I forgot to tell you last time, the determinant of F gives you the change of volume. So my F is current volume over the reference volume. So it's a volume ratio, or it's mass ratio, mass density ratio if it's a mass continuum. of course, in lattice continuum, well, instead of this, we would have this. That is number of lattice sites in per unit volume in reference configuration, and the same number in current configuration. Okay, so then we said a little bit more about kinematics of diffusion in crystals, right? We had a diffusion flux, and see, because I have new lattice created, so during the deformation process, my new lattice is created here. What is the reference configuration for that? Well, I need to formally. Well, we're not going to do that, but I just need to know that I have my quantities defined. Well, if I say that new lattice is created with continuous lattice density, continuous deformation gradient, and continuous vacancy concentration, then I can integrate back in time. See, I do have velocity gradient because my v is function of small x and time, so I can always take a gradient of v. So I can integrate back in time and get this formally, mathematically, reference configuration for this point here of a newly created lattice. I have diffusion equation, and one point that we emphasized, creep deformation rate will be, you can only assign one tensor to each grain, because the creep comes from creation of new lattice and destruction of lattice, right? So, it's not a field, it's not a variable within a grain, it is a constant for a grain. So, in a polycrystal, it is a piecewise constant field, creep deformation rate. Okay, we discussed basic properties of stress tensor. We related, where is my, stress to the tractions on the surface with normal n. Stress is symmetric, and because of that, we can, when we double dot it with deformation rate, that's the same as double dotting it with full velocity gradient, and velocity gradient is decomposed into symmetric part, deformation rate, and rotation rate or spin, skew symmetric part. So then finally we are done with kinematics. Well, we are not done, but we have finally moved into dynamics and started using forces. So we used balance of momentum, of linear momentum, to derive governing equations. So for all continua, velocities are governed by those Cauchy equations of motion. Now, we imagine that somehow we can substitute here stresses, 6 independent stresses, for 3 independent velocities, right? These are 3 equations. This is a vector equation, right? And solid mechanics, fluid mechanics, that is a fundamental equation which comes from a balance of linear momentum. Now, with that in mind, we have defined strong form, 2 types of strong form. Strong form consists of differential equations for our variables, and I can consider velocities and mass density as variables, or I can consider just velocities as variables and use mass conservation as mass balance as additional constraint. But in any case, I have differential equations, I have initial conditions, and I have boundary conditions. And boundary conditions, those given in terms of my primary variable, which is velocity, I called essential, and those given in terms of gradients, I called natural. Again, we imagine that I can somehow, that I have some constitutive equation in which I can express stresses in terms of velocity gradients. For example, so then we derived, we introduced the concept of weak form. Now, weak form is important for two reasons. One of which I told you last time, the other one I didn't mention. First is to get our numerical method, finite element method, we need to recast our problem in the weak form. But the other more important problem, more important application, if you start from balance of energy or rate of energy or power balance, you can reformulate your power balance using principle of virtual power and get your weak form directly without the strong form. And that is probably the most efficient and most rigorous way of deriving your governing equations. We will do that today for one example. But meanwhile, I started showing you that weak form and strong form are equivalent. And last time I showed you that if I start from strong form, so I start from my governing Cauchy equations of motion, I multiply them by my test function, and test function was something arbitrary except where I have prescribed v. There, at those points, my v tilde test function or virtual velocity, there it must be 0. Everywhere else it could be anything. It could even be discontinuous, it could have, well, integrable singularity. All that is required from this test function is that it is 0 at those particular points where my velocities are prescribed, and that it is integrable over the domain. So I do that, and I do some manipulation. Well, when I multiply my governing equation with v, I integrate over the domain, and then I do some manipulation here, and I end up with the weak form, or principle of virtual work, which says that real forces, these are prescribed tractions on ST, these are prescribed body forces, these are inertial forces. So the work of real, actual forces on virtual, or I should say power expanded on virtual velocities or rate of work, is equal to the work of internal forces, real internal forces, which are stresses, on internal kinematic variables, which are gradients of velocities. Now, well, I want to go backwards. Well, here's my same weak form. Well, if I now write this t as n, so ti, I can write as ni sigma ij, and it's multiplying v tilde j, right? So I have ni sigma ij v tilde j. So this is n dotting something on the surface, and I can change this integral to s because v tilde is 0 on the other part, right? S consists of SV, let's say from here to there, and ST, right? but on SV, V tilde is 0, so I can do the whole integral here, doesn't make any difference. And if I do that, then I can transform this. This is n dot sigma dot V tilde, right? So n dot something is the gradient of that same thing. So this will go under volume integral as gradient of sigma ij Vj, and that gradient is sigma ij, actually not gradient, divergence, sorry, sigma ij Vj, comma I, which then I change into sigma ij, comma I, Vj, plus sigma ij, Vj, comma I, right? And this term is this divergence sigma and rho b and dv over dt, and this term here it is, sorry, actually I went backwards from this. These are prescribed tractions, right? So when I go backwards from this, well, I will get a term n sigma, which says that the tractions must be equal to the prescribed tractions. N sigma must be equal to the prescribed tractions on ST, and I get my governing equations. So the weak form and strong form are equivalent.
You don't have the closure in the weak form?
No, closure you don't need yet. To get a full, to implement it, you need closure. But here we are keeping this stress as just stress, right? So this is sort of a version of the weak form where we don't need. Right, you put the closure in here. Right.
In terms of the velocity gradient?
Yes, yes, you would just well substitute the stress. Okay. So now the next step in our study of continuum mechanics is to see what are we going to do with this deformation gradient, right? Or more precisely, what are we going to do with these measures of deformation? With these are called right and left stretch tensor, for obvious reasons, right? So that is, how do we define measure of strain? So let's first see. Let's look at an element which has a direction of eigenvector of u and magnitude d capital X. So dx is r dot u by dx. When I substitute this dx here, I can pull out the magnitude. So it's r time, and u is some lambda u alpha only when this alpha in this counting, only u alpha will survive, right? Only one will survive because dot products are, two of them are 0, only one is 1. So I have lambda alpha dx v alpha. So this this operation stretches the element by lambda alpha, and it rotates from u alpha to v alpha. So if I want to express my strain tensor in terms of with respect to original configuration, so I would like to express it in terms of eigenvectors of u. That is, the u is the original position of a fiber, right? Like here. Cannot see my cursor. Where is it? It's here. Okay, so u, these are my u's. These are original positions of fiber, and v are the final ones, right? Like here. So I want to express my strain in my strain measure, my strain tensor, in terms of these dyads, u alpha, u alpha. Now, I want my measure of strain to be consistent with the definition of small strain. And you have all seen small strain, if you write it in components, epsilon ij, 1/2 ui comma j plus uj comma I, right? So this is my small strain, which means that when those principal stretches lambda go to 1 and r goes to 0, so no rotation, my strain measure must converge in the limit to small strain, which in turn implies that this function of lambda must go to 0 when lambda goes to 1, and its first derivative when lambda goes to 1 must be 1. Meaning when it becomes small, only first derivative is there in if you do Taylor expansion like here, f of lambda in the vicinity of 1 is f of 1 df over the d lambda at lambda equals 1 by lambda minus 1. So, and then second derivative 1 over 2 factorial and so on and on. You know Taylor expansion. So I want this term, this term, f of 1 will be 0, and I want to have 1 by lambda minus 1, that is lambda minus 1, that's a stretch, and that converges, that's consistent with small strain. So three most common choices for this function f of lambda are 1/2 lambda square minus 1. You see, for lambda equals 1 is 0. Its first derivative is just lambda. So when lambda goes 1, its first derivative goes to 1. Biot strain, that's just lambda minus 1. First derivative is 1, and when lambda equals 1, it's 0. F is 0. And there is also log strain, which we, and you can see when lambda goes to 1, log is 0, and its first derivative is 1, because its first derivative is 1 over lambda. Okay, so now if I want to write that in in tensorial form, my green strain will be 1/2 f transpose f minus I, or 1/2 u square. Now, for symmetric tensors, such as u, I have no problem writing u square. There is no confusion with the meaning, because I tend to think of u, and this is the best way of thinking of it, as a sum lambda alpha u alpha u alpha. These are unit vectors, right? Alpha goes 1 to 3. So u square will be sum of lambda alpha square u alpha u alpha. Any questions? Yes.
I want to understand this E and epsilon. E is the strain in whole body and epsilon is
Okay, epsilon is my small strain. You have probably seen in your undergraduate strength of materials definition of small strain, but that's just a small strain.
small element.
No, that's where, see, where those gradients are small. But strains are not always small. Deformation is not always small. So we are now looking for a measure. How do we measure strain when it's not small? So it turns out there are many different ways to do it. But one important condition is when we take a limit of small strain, those measures of finite strain, of large strain, have to go to the limit of our definition of small strain.
This is in the Cauchy limit.
Sorry?
This is not the second Euler-Kirchhoff.
No, these are stresses. Euler-Kirchhoff.
That's also stress.
Well, Euler-Kirchhoff stress will be power conjugate to green strain, but that's whole another story. Well, that has well, we don't need that now. So the general idea is this: how do we measure large deformation? For small deformation, it's easy, right? You just take those gradients, and you take the symmetric part. But what do you do with large deformation? Well, we do have this stretch tensor U. And we know that that tensor contains all the information that we need. But how do we define a strain? We want our strain to be consistent with small strain. So if you think of arbitrary deformation, large deformation, and now take a process in which that deformation becomes smaller and smaller, right? My definition, our definition of strain should converge to the small strain definition in that process. And that is how we accomplish that, right? We write everything in terms, well, on the basis U alpha. Something is happening. We write everything on the basis U alpha, and we demand that this function, and on that basis, those three eigenvalues are everything that we need, right? So we take function of those of each eigenvalue, and we demand that that function is 0 when stretch ratio is 1. Well, obviously, no deformation, right?
In that case, can I say like this small strain correspond to lattice distortion and this large strain correspond to my rolling deformation?
It might be the case in that particular case. You might get small strain. One deformation mechanism might give you small strain. The other one could give you large strain. So in elastoplasticity, elastic deformation is always small. But you have to combine them together. That's not simple. That doesn't help you much because plastic deformation is large. So you have to treat whole deformation as well as large deformation. But as you start deforming, right, even your plastic deformation is small in the beginning, and then it becomes larger and larger. So you want to have consistent mathematical description, consistent measure of strain, which for small strain will reduce for our definition of small strain. That's the idea. And obviously there is more than one way. You take function of those stretches, and you demand that it goes to 0 when stretch is 1, and its first derivative goes to 1 when the stretch is 1. And that will ensure that you are consistent with the definition of small strain. And these are some of the strain tensors used: green strain, bias strain, log strain. And you can define them in terms of our tensors like this. Bias strain is just u minus I. I is the unit tensor. Right? And log strain is log lambda u alpha. See, I'm free to write this because u is a positive definite symmetric tensor. It has positive eigenvalues, and I can write u in its eigensystem in terms of 3 eigenvalues. So when I write log u, what's the log of a tensor? Well, for these tensors, I have no doubt what the log is the sum log lambda alpha u alpha u alpha.
U alpha is unit vector or is it U alpha?
I'm sorry?
Is the U alpha unit vector or is it
Capital U is a tensor, rank 2 tensor, right? Small u, these are eigenvectors. These are eigenvectors of u, or principal directions. If you want more physical expression, you can call them principal fibers. These are the fibers that are only stretched by you. When you act on them with this deformation, they are only stretched.
But in the small dx element,
Well, it varies from point to point, right? So each point, this u is a field. This tensor u is a field, and it varies with position and time. Online questions. F, I have answered that. How dft lambda goes to 1 for lambda? How? Why is the second order differential eliminated in green strain? To make it simple. There's no other. We have options how we define our strains. So all we need to do is to satisfy these conditions, right? These are the conditions that we need to satisfy. So all those definitions would work. You could add higher order terms here, if you want. But the point is, those higher order terms, when lambda goes to 1, go as square of the small quantity, right? So they are infinitesimals of higher order, and they will be negligible. As you approach the small strain, they will be negligible. So see, the only term that the first order infinitesimal is this term. This term is 0, right? This is the first order infinitesimal. This is higher order. So this goes to 0 much faster than this. This one goes to 0 faster than this one. Okay, I hope I answered those questions. Lambda, well, could be larger, could be close to 1. That's a stretch ratio, right? It's a new length divided by the old length of the fiber, of the principal fiber. You can get, it could be strain of order 100% would correspond to lambda of approximately 2, right? Yeah, 100% strain. When you double the length, right? That's lambda equals 2. Lambda equals 1, well, corresponds to no deformation, no stretching. When lambda is smaller than 1, that corresponds to compression. But it has to be greater than 0, obviously, because you cannot compress finite length into 0 length. Right. So lambda goes from 0 to infinity, right? There is no upper limit.
if there is a, if lambda is large, accordingly we have to take the number of terms the Taylor series.
Well, it depends whether your physical process requires it. Right. So you could take a higher order function here for say for green strain.
But in
No, but are you asking about why don't we need this here, or are you asking why I only have lambda square here? What are you asking?
Yes, I'm asking the small strain is when lambda is closer to 1.
Yes,
Small
yes,
strain when lambda is closer
yes.
to 1. So if lambda is much larger, then there will be other terms in the Taylor series expansion.
Yes, but yes, here, well, this log strain. If you do well, Taylor series, you will have well, all sorts of terms to infinity, right? But I don't care about them, because all I require is that my measure of strain in the limit of small strain, that is when lambda approaches 1, it has to be consistent with small strain definition. That's all I require. For large strain, the options are limitless. Right, right. You could use any definition you want. Yeah, because basic information is in this U, right? Now, how you want to represent that deformation, that's up to you, and it's usually dictated by well, different mathematical needs. Okay.
If the vacancies are generated during the process of deformation,
I'm sorry?
then you are only stretching. So stretching, it can stretch only when the dislocations are created. This metal cannot create.
Depends on the material. You can stretch with well, by diffusional creep. Right, diffusional creep without dislocations. Right, diffusional creep takes place by diffusion, and lattice growing at the end of grains, right? So you can get stretch ratio 2, 10. Well, some soft metals may creep a lot. Also for materials like polymers, well, there are no dislocations. That's a completely different deformation mechanism. So yes, high temperature. Yeah. Okay. So what I would like to do now, I'd like to take a general view. After this slide, we will make a break. Actually, I have 2 more slides. This one. Okay, let's see, and I have 6 minutes. Well, I've given myself 6 minutes. Yeah, that's but your stretch ratio will be high. Your lambdas could be high, but deformation will be purely elastic. Oh yes, you would use one of those definitions of strain, but see, you do experiments, you measure stress-strain relationship. Which strain are you using when you're interpreting your experiments, right? You can use any of those 3 that I've shown you, and there are more, but then you have to be consistent. Keep using that one in your constitutive law. So the choice of strain measure for large strain is arbitrary. You can use any of those 3 that are listed here and some other measures. The point is that all information is in U. This strain is just the way we interpret that is consistent with our intuitive understanding of small strain, small deformation. That's the whole point here. Okay, so let's try to think in more general sense. I'll try to derive governing equations here in rather systematic way for some general undefined problem. So, well, I have a material. It has to satisfy mass balance, and we are talking mass continuum here. Think of a fluid also you can think of a solid, doesn't matter. So there is a mass balance. Okay. Now, each point x at a material has some internal energy. Part of that energy is elastic energy that is associated with the formation gradient. And let's say material has some state variables. I need state variables. Those state variables could be dislocation densities, could be composition, concentration of, say, carbon atoms in zirconium carbide, could be phase variables, right? So some extra variables which I need to solve for. These are unknown fields. And let's suppose, let's imagine that I have that specific energy. That's energy per unit mass. I could do that per unit lattice too, but let's now stay with mass for the moment. So suppose I have that, or I can get it, doesn't matter how. My primary kinematic variable would be velocity. Velocity gradient or strain rate, measure of strain rate, will be primary internal variable, but I will also have the rates of internal rates of those state variables, C1, C2, and so on and on. So in general, I should be able to write dissipation. Now, when I say dissipation, what does that mean to you? Sorry?
Energy dissipation.
Distribution, radiation, distribution.
Okay, let's make more precise definition. Each point, each part of the material has its energy, free energy. When I, or let's call it potential energy. It could be chemical, elastic, whatever. When I transform that into heat, that's called dissipation. So dissipation is transformation of potential energy into heat. So it leads to increase in temperature, right? So this is dissipative process is, say, friction. I'm doing work using forces. I'm creating heat. Motion of dislocations is dissipative process. Diffusion, well, is dissipative process. You lower the potential energy of the system, but that extra energy goes into heat, into thermal energy, which you have to take away then. So potential energy into heat.
So any irreversible process is
Sorry?
any irreversible process where you generate.
Yes, yes, yes. So that's what we mean by dissipation, and that's why we distinguish between energy that is contained, specific energy, and dissipation or dissipation rate, if you want. So that dissipation rate will depend on deformation rate, and there will be some power conjugate tau. You can think of tau as viscous stress. That's intuitive, right, in fluids. And those other rates, let's assume these are all dissipative, well, internal variables, they will also have their power conjugates. And I'm writing them here as, well, as a vector. Does that mean only part of the energy is stored in the form of dislocations or other state variables? energy can be stored as elastic energy. It can also be stored as chemical energy. If you have diffusion of, say, component B through component A, the concentration of B in matrix A makes a difference in well, chemical energy. Also, phase stores, formally, phase stores energy. Well, one phase may have higher energy when it transforms. It may dissipate that energy. So it's not just dislocations. There are other state variables plus elasticity. So anything that is stored and can be obtained back from the material, that's the potential energy. Okay, so see, when I write this C, I mean well, some sort of vector, but not necessarily vector in three-dimensional space, right? It depends how many of those variables I have. So this is just a short writing instead of using matrices. Now, no, second law of thermodynamics. So dissipation for processes which are isothermal and for processes where temperature is controlled, well, from the outside, which is just like you don't have to have constant temperature. But if you're controlling temperature, you are taking heat and putting it in to keep temperature, well, as you want it. It works thermodynamically just like isothermal process. So for those processes, second law requires that your dissipation be non-negative. That's you transfer potential energy, which is low entropy form of energy, into heat, which is high entropy form of energy. So that's why that is. So so you need to get your closure or constitutive equations to find those, right? You need constitutive equations. Okay. Well, imagine that you have a zirconium carbide, piece of zirconium carbide, and somewhere on the left you have lots of carbon, so all sides are filled, and on the right it's zirconium carbide 0.5. So well, something like this. Zirconium carbide 1, and here I have zirconium carbide 0.5, meaning that half of the sites where carbon should be.
Higher potential to lower potential.
I'm sorry?
Higher potential to lower potential.
Yes. So this sample, if I start like this, starts with high potential energy. It will lower its energy by diffusion of carbon towards this side until everything becomes uniform. And that's the lowest energy. Now, where does that energy go? That energy is transformed into heat. And you may want to keep temperature constant, or maybe you're not keeping it constant, whatever. But this potential energy is transformed into heat. Diffusion is a dissipative process. Okay. Okay, so where was I? I think we should make a break here, and then we will write power balance. So this is a good place to make a break. 5 minutes. Oops. Can we go back to the slide? Yes, that's it. Excellent. Okay. So let's restart this. What we're going to do now, we're going to write power balance. So external forces, where are they? Here they are. These are external forces on the surface and external body forces, right? They will increase the energy, this is potential energy, this is kinetic energy, right? And this is heat. This is heat taken away, or in other words, that is our dissipation. So that's our power balance. Now let's look at this time derivative. We will use transport theorem. So time derivative of this integral is integral over rho by time derivative of this, right? So let's do the time derivative first of potential energy and then on kinetic energy. So to get time derivative, well, potential energy is a function of the deformation gradient and state variables. So I'll have del u over del f, or if you want to write this in terms of components, it will be del u over del fij by dfij dt, right? So, and that's a double dot product, del u over del f by time material derivative of deformation gradient, and that material derivative, this one, is, we showed earlier, velocity gradient by f. So if I write this in terms of components, I'll have the ij component of del u over del f by ljk fki, and then if I move this fki to the left, this will become a product f dot del u over del f, double dotting L, because this is kj component, this is jk component.
What is a double dot?
A double dot, that's a double contraction. So when you double dot two tensors, A double dot B, that's Aij Bji, right? And you sum over all the indices. Okay, so now when I substitute that here, here's my cursor. Okay, I will substitute that here. And this quantity will be my Cauchy stress, non-dissipative stress, non-dissipative part of stress, because that's what does work on velocity gradient. If I add this dissipative stress here, my total Cauchy stress will look like this. A rho, that's this rho here, F del U over del F plus this tau. And tau I get from constitutive law. That's what does work on, that's what expands power on the velocity gradient. Now, I also need to take time derivative of U through state variables, right, Xi, and that will look like this, right? Del U over del Xi over del T, and the time derivative of 1/2 V square is minus dV over dt dot V, right? So let's now account for all the terms. I will put external terms on the left from this expression. I will put external terms on the left. That's this one, and the body force or inertia. Internal terms, well, in the volume, this one, let's denote them like this. This one and this one will give me stress by velocity gradient, and then with state variable rates, I have psi from here, and I have a rho times del U over del Xi. This is my power balance written in a way that I can now use to write the weak form of the problem directly. I can use this to formulate the principle of virtual power. Okay, how will I do that? I have external forces doing work on these are actual forces, but if I replace my kinematic variables V here with virtual variables, and I do the same thing with my internal rates, this statement will become the statement of virtual power. So external forces expand power on the velocities, and that is equal to the power expanded by internal forces, which means stresses on velocity gradients, and internal generalized forces on rates of change, on internal rates of state variables. So here we are. The same statement as before. Well, I just written acceleration here as V dot. So this is power balance, and this is principle of virtual power. I only replace this. If I write power balance properly, I can just replace those velocities with virtual velocities and those deformation rates with virtual deformation rates, and those real, actual state variable rates with virtual ones. And I have my principle of virtual power, which is in fact the weak form of the problem. Now, from weak form, I get the strong form. How? Well, I will write this sigma. This is sigma ij, and then V virtual j comma I, which is the same as sigma ij vj comma I minus sigma ij comma I vj, right? This one will go to the boundary, right? This is divergence of sigma ij vj. So it becomes n dot sigma, right? and if I put it on the left hand side, it's with a minus sign. This one stays in here, and it's a divergence of stress by virtual velocity. So that's this one. This one. And the other terms I copy, rho b, rho v dot, and this remains, well, in the volume. And now I make the following argument. Weak form says that this integral equation has to be 0 for arbitrary value of my virtual velocities. And because they are arbitrary, I can vary them independently on the surface and in the volume. Also, the variation in V is independent from variation in Xi. So, from the fact that this has to be valid, or if you want, well, I can write minus here and call it equal to 0, right? So this has to be 0 for arbitrary V tilde and Xi dot tilde. I can just vary Xi dot tilde and claim that this has to be 0 always. So my Psi has to be equal to minus rho del U over del Xi. But I can vary now V independently in the volume and on the surface S. From independent variation in the volume, I get governing, I get Cauchy equations of motion. This has to be 0. And from independent variation on the surface, I get boundary conditions. My normal dotting stress gives me tractions. So, see how I derived my equations using weak form first. I just did power balance or energy rate balance. Then, if I write it properly, I can write principle of virtual power, and from there I get strong form. So from weak form, I derived the strong form. This is a very useful way, and very rigorous way, of deriving equations, because if you do this way, you will know precisely what does work on what. You will not make perpetuum mobile. You will not violate laws of thermodynamics. So your mathematical model will be consistent with physical reality. You will find there are many ways of there are other rigorous ways, but very often in literature you will find ad hoc models which sometimes do not satisfy laws of thermodynamics or not even laws of motion. Okay, but you see from here there is a bonus. What I have achieved here, I have obtained my power conjugate, which was unknown, right? It's partial of the energy density with respect to state variables. Or, well, alternatively, if instead of specific energy given per unit mass, I use energy density, use script, which is given per unit volume, in reference configuration, then that is rho naught U, and I can write this as 1 over the determinant of deformation gradient. This F is determinant of the deformation gradient tensor. Okay, so with this, we're more or less done with general continuum mechanics. it remains to discuss our numerical method, which will be the finite element method. But before I go there, let's hear some questions. Any questions about this? Mm-hmm.
So, how to summarize this part?
On the slide before, we formulated power balance.
Right.
So, from power balance, I introduce virtual functions or test functions, virtual velocities and virtual state variables. Those are variations. And from power balance, I formulate principle of virtual power, which is my weak form. And then from weak form, I derive the strong form.
How does that help us?
Well, here's how it helps you. You don't know this. This is new information. See, you didn't know what does work. What does work on your state variables? Say concentration, right? You have a diffusion, so you have a concentration of vacancies or some element in the lattice. What is the generalized force? What does work?
I cannot see the slide.
Oh, why aren't we seeing the slides? Yeah. Okay.
So in the power balance, we had work done due to surface traction.
Yeah.
Then we had body work done potential energy,
Yes.
and then you had the dissipation part.
Yes.
Okay, so this was
But you don't know what this is, right?
Psi is the force. It is a generalized force.
Yes, generalized force, but you don't know what that force is. I mean, how do you get that force?
but where is that force act? I mean, upon which is this force acting?
That is generalized force which induces diffusion,
Okay.
right? So it acts on the rate of change of your state variable, and if your state variable is concentration, right? That's what does work on change on concentration. So
Basically, the generalized force comes because of the U, the potential energy.
yes,
Because of the
yes,
energy concentration.
yes. So we now know that to get that generalized force, you need to find where is my cursor? Well, you need to compute this or this, right? And now this is rather general and simple term, but when you start putting in different variables, say different concentrations, phase fields.
So in this form, you can take into account all those other factors.
Yes.
Variables
Yes.
Which may contribute to your potential energy.
Yes, yes. This tells you what your governing equations are, right? Because now you will write in addition to this governing, this equals 0. This is your Cauchy equation of motion, but you will have a constitutive law, dc over dt equals some, let's call it some mobility by psi. Well, you need to know what this psi is, and this is now constitutive law, right? But this is now governing equation which is coupled to this one.
Right.
So this is how you derive governing equations when you have multiple state variables, phase fields, and everything that is going to be there.
Couple your system
Y-
to physics.
yes, yes. And that's how you know what equations govern evolution of, say, phase fields.
Right. So that's why you need the weak form
Yes.
to do this coupling.
Yes, that's the clearest way. People do different ad hoc, and they often make serious mistakes. But this is a clean one because you write your energy balance. You go straight to the weak form, and you know what does work on what. You know what power conjugates are. So there's no confusion, and you see clearly where the coupling comes in. So when we will do that, not today, but in the next lecture, we will do it for phase field problems. So we'll see how it works. Any more questions before I move on to finite element method? Okay, so finite element method is based on interpolation, and I think it's best to work on this problem on simple example. And let's do linear elasticity, and let's say small deformation. Elasticity is often small deformation. And let's neglect the change in mass density, right? If you compress elastically, mass density doesn't change much. So these are my governing equations, right? But when I substitute stresses as a linear combination of strains, this C, that's elasticity tensor. It is rank 4 tensor, which has number of symmetries. So I'm sure you've all seen this.
I just have one silly question. So this inverted triangle is the Laplacian, right?
No, this is gradient.
Yeah. So this is like gradient.
So this term is ui comma j plus uj. No, sorry. This term is ui comma j on the basis ei ej, and this term is uj comma I on the basis ei ej. That's a gradient operator.
This is like displacement.
U is displacement, yes.
But this is the symbol for the Laplacian, right? So this is like del del x.
No, well, no, for Laplacian we do either this or that.
Okay,
Yeah. Okay, so this is a standard definition of small strain, right? So I connect my stress to strain via elasticity tensor, right? Which has certain symmetries. You can flip first two indices or second two indices, or you can flip first two with second two, right? Major and minor symmetries. But when I substitute that here into the governing equations, and I substitute definition of strain, I'll get second order partial here in terms of displacements. So substituting stress, substituting in strain, this is what I get. This is in terms of components. So this is my strong form, three vector equation or three scalar equations for components uj. I have
double differential u double dot.
Yes, that's acceleration. Yeah. Oh, that's v dot, right? Well, if you have a velocity, time derivative of velocity, that's the second derivative of displacement. Okay, so I prescribe initial displacements These are initial conditions. And then I have boundary conditions. On the part of the boundary SU, let's say part from here to there, this is SU, I have prescribed displacements, U hat, and on the part of ST, well, I prescribe tractions, so N dot stress, and stress is C double dot U del. So essential boundary conditions are given in terms of displacements. Natural boundary conditions are given in terms of gradients of displacements. Is that clear? Any questions here?
The last, the third condition. Repeat again.
What, this one?
Yeah.
This is stress. And stress is C double dot strain, right?
Let us wait for the slide to come back.
I'm sorry? Aha. So, you don't see the slide. Let's see the slide. Okay, so this here is the stress, right? N dot sigma is traction, right?
Right.
And sigma stress is C double dot strain. But C has this well, symmetry. You can use KL or LK, right? And that means that instead of strain, you can take the full gradient here, not just the symmetric part of the gradient. It doesn't matter, right? So your natural boundary condition is given in terms of gradients of displacements. Make sense?
Kind of.
Okay. It's just a short. There's lots of details, but tractions are related to stresses.
That I understand.
Stresses are displacement gradients, small strain elasticity. Yeah.
EDC is essential boundary condition.
Yes. This is some prescribed displacement. This is essential and natural boundary condition. So the essential boundary conditions is the one that affects our test functions. Yeah, when at those points where essential boundary condition is prescribed, those points here, my test functions must be zero.
That function should satisfy the essential boundary.
Yes,
Not
not
natural.
natural. Yes. Well, apart from that, test functions are arbitrary. Well, my weak form. Question?
No.
Any more questions? My weak form is now. I can just write it directly as principle of virtual work. I could derive it from strong form, but I could just do principle of virtual work, which says the work of external true forces, that these are the real forces, on virtual displacements, sorry, not here, here, is equal to the work of stresses on strains or just deformation gradients, and if I replace this stress here with C double dot del U, or because of this symmetry here, well, I can write it del U double dot C. This is stress, right? These symmetries will help a lot. So now my weak form has a quadratic form here of displacement gradients, except that these ones are real and these are virtual. These are test functions. So I can use this to directly develop finite element equations, and this whole process is depicted here in this one slide. So finite element method in one slide. I discretize my domain, right? I have a certain domain and I put nodes and elements, right? And the most important part of finite elements is that discretization. I will be talking about that. But the important part is interpolation. So my unknown variable is u. I want to represent that variable as the linear combination of nodal values and interpolation functions. Now, see, if I do that, I can easily make sure that this interpolation is exact at nodes. If I just make my interpolation functions have value 1, psi alpha have value 1 at node alpha and 0 at all other nodes. So in 2D, in plane, for example, if this is node alpha, this is like a tent function, right? It has value 1 here, but all the other nodes, well, it has value 0. Then you see, if I substitute here coordinates of my node alpha, I will get that my displacement is equal to the nodal value. Because in this sum, only the, if I put x alpha here, these are coordinates of the node alpha, only alpha equal beta survives. All the other functions are 0, right? And I'm left with u of x alpha equal u alpha, where u alpha is the nodal variable. So you see, I'm expressing a function with nodal values using interpolation. And I will do the same thing for my test function. Same interpolation here. Now, notice that I'm confining time dependence to nodes and space dependence to interpolation functions.
Right. So this u beta, these are some coefficients?
I'm sorry?
The u beta.
These will be unknown that I will get from numerical method. These will be nodal values that I will be solving for.
These are some numbers, right?
Yes, but well, I don't know them a priori.
Okay.
Right.
Yeah, I don't know the numbers, but these are some coefficients.
That's the nodal value of displacement.
Right.
Right. In mathematical problem, your displacement is an unknown function. In numerical problem, you have nodal values.
Right.
So these are nodal values. And this is function. If I interpolate between nodal values, I get a function in space. So I do the same for my test function, and because of this separation, nodal values vary in time, but my spatial interpolation does not. Then gradients will only have gradient of test function, and time derivative will only have time derivative of nodal values. Sorry? Question of line. Does the interpolation vary linearly from one over? Linear interpolation is the simplest one. So it's not always the best, but is typically it's not bad. How I'll talk later more about interpolation. In 1D, it's simple. If you're interpolating through two points, you can only draw a straight line, right? to do any higher, any polynomial of higher order, you will have to have, well, multiple points, right? But we'll talk more about that. Well, that will be clear. So they don't have to be linear. Well, I'm just drawing them linear because it's easiest to draw. Okay, so the next step is I take my principle of virtual work here, and I substitute this interpolation. And let's for the moment forget all these other terms. Let's look at this main term here. I have gradient of u. That means I have the sum u beta gradient of psi beta. And I have here sum of u tilde alpha gradient of psi alpha. So I can pull those sums outside. Here's the sum over alpha, u tilde alpha, sum over beta, u tilde beta. And these are the gradients, psi alpha, psi beta. And I have this C, ijkl. So you see, I have pulled out the sums and nodal coefficients out of the integral. What remains under the integral is known, because interpolation functions are known. And material properties are known. Yes?
No, I mean, you are replacing some integrals with summation.
No. Well, I have integral here. Well, I have summation here.
Okay, those summations are coming in.
Yeah, yeah. I'm just pulling out the sums and constants out of integrals. So, yeah, so this is this integral, this one.
Vectors and tensor converting to summation.
Yes, and I'm using summation notation, right? But this is what you get. You pull out nodal values of test function and corresponding sum, and nodal values of real displacement and the corresponding sum. At whatever remains here is known or can be computed, right? You have integral of gradients of test functions. You can ask your computer to do that. You can program it. And this we will call element of stiffness matrix. I'll put upper indices well corresponding to nodes, and lower indices, upper Greek indices correspond to node numbers, lower indices corresponds to components in three-dimensional space. These other terms are rather simple. When you substitute this, you get with and this, you get expression like that with accelerations and free terms here. Okay, where am I writing? I don't see my. I cannot see my cursor. Do you see? Aha, on the right. Here it is. Yeah. Okay. So from this one and from this one, you will get the forcing terms. And they will go with the test function. This is all under this sum. So when you pull everything out, you have sum over alpha, test function, and here you have a mass matrix by acceleration, stiffness matrix by displacement, minus forcing, free terms. And this has to be 0 for any u tilde. Now, if it has to be 0 for any u tilde, I can take one of those equal 1, another equal to 0, and show that the value of this thing in these brackets has to be 0.
Why does it have to be 0?
That's the weak form here.
Okay.
Right.
And I forgot what is beta?
Beta is counter.
Beta is what?
Beta is the counter for sum over beta, u beta, c beta. It counts the nodes.
Number of nodes.
Yes, alpha and beta count nodes.
But why do we need two counters?
Because nodes interact. Right, you need count, they're not decoupled.
So every node has, let's say, say two counters. So let's say node, let's say some.
No, node doesn't have two counters. Well, I write u as a sum over beta, and I write u tilde as sum over alpha. This is just a counter. I can call them anyway.
I understand, but what I don't understand is why do we need two counters?
Because, well, these are different functions.
Okay.
This is a counter for displacement, and this is a counter for virtual displacement.
Okay.
So when you substitute it, by default they're different, right? There is no reason why they should be the same.
L is also counted. U and
L and I are lower indices. They go from 1 to 3. Right, this is the upper indices, upper Greek indices are counting nodes, and lower indices are counting directions in space. So, because this has to be true for arbitrary u tilde, that means that this part has to be 0. Or written this way, it looks like this. Or in matrix term, you will write it like this: m times u double dot plus k times u equals f. And by this I mean a column, long matrix of all the same for you. And these are this would be finite element formulation for elastodynamics. If I have strictly elasticity, quasi-static processes, acceleration goes to 0, and these are your standard finite element equations.
K is the stiffness matrix?
Sorry?
K is the stiffness matrix?
K is the stiffness matrix, yes. Okay, now,
These equations will come in a nightmare.
sorry?
Right?
Sorry.
lot of work is required to drive this equation.
Yeah. Well, I don't know shorter way to get from point A to point B, right? Well, maybe there is, but it's not useful to us, because we will need to do that for problems where, in addition to those displacements and velocities, you have phase fields, you have concentrations. So, but we need to looking into details.
Yeah, yeah.
That's lots of bookkeeping here.
Right.
But try to understand this physically and qualitatively, what we are doing.
Right.
Right. We substitute we replace the function in the weak form using interpolation in terms of nodal variables. Then when we put it into the weak form, we dump all the known coefficients, including interpolation functions, into finite element coefficients, stiffnesses, forces, mass, and we get algebraic equations for elastostatics. We get linear algebraic equations, system of linear algebraic equations for unknown displacement. For elastodynamics, we get a system of ordinary differential equations in time for nodal variables. So now, and they are coupled.
I just have one question. So this U that you have written in the last equation, this U is U tilde or normal U?
Which equation?
The equation you just wrote.
This one? Oh, this is this is unknown U. This is a real displacement. Well, look here. Well, I only have U tilde here. This is the last trick. Because my weak form has to be true for any U tilde, for arbitrary U tilde, I can claim that this thing that multiplies U tilde has to be 0.
Right.
And then my next equation doesn't have U tilde. It's gone. So that's the funny thing with those test functions of virtual displacement. We introduce them. They are silly, arbitrary, mean nothing, and then we use the fact that they're arbitrary to get our equations, and we throw them away.
So this is U.
Yes. Yes, we are solving for real displacements. Okay, now there were questions about interpolation. Let's see. I think I'll have time to cover, well, interpolation. Okay, so we use polynomials, and we typically use natural space. Oh, I don't have a slide with that. Sorry? Ah. So I would express this quad element. This is a quad element, 4 nodes. It is natural space with coordinates c and eta, where c and eta vary from -1 to 1. And so that's how we usually write our elements. And then we will have a mapping, 1-to-1 mapping. Each point here would map into a point here. And this mapping would have to be 1-to-1. So this c and eta, well, are natural coordinates. How can I write, well, those polynomials? Well, if you write a polynomial of certain order, there is a number of unknown coefficients. Well, how many of them you can solve for? That depends how many nodes you have, right? So if I have 3 nodes, I can only have those 3 terms. This is so-called Pascal triangle, 1 xi eta, then quadratic terms xi square, xi eta, eta square, and so on and on. For 3D, you can imagine Pascal pyramid, right? But this is what I can do with 3 nodes. My polynomials could only be linear and xi and eta. With 4 nodes, well, I will have a term xi eta. And notice that I have to treat xi and eta equally. There is no reason why, well, I should prefer one over the other. So for full quadratic element like this full quadratic element has 9 nodes, and I would use all those terms. So my highest order term will be fourth order term, which is biquadratic term in Xi and eta. It turns out that it can be shown that this node doesn't do much. So more common is 8 node quad without this term, right? That's up to here. Even more common is 6 node triangle, which includes all the nodes up to here. Important point here is that accuracy of finite elements depends not on the largest power in the polynomial, but on the completeness. So notice that my 9 node quad here and 6 node triangle have the same completeness. Completeness is the highest order full polynomial. So for both 9 node quad, I have all these terms, but my highest complete polynomial is of order 2. 3 is not complete. I don't have these terms. 4 is not complete. So for this, my completeness is 2. But so is for this one. And I have only 6 nodes. And with triangles, I'm much more flexible in meshing and remeshing, making denser mesh, coarser mesh, changing the density of the mesh. That's much easier with triangles. So this is probably the most commonly used element. This one and this one. A linear triangle and quadratic.
How about square?
Huh?
I've been told that square mesh is good and triangular mesh, I've been told that it is stiff. People don't like the triangular mesh, I've been told.
What, linear triangles?
Yeah, linear triangles.
Yeah, this is the lowest possible order. Linear triangles are you have to have very fine mesh, but quadratic triangles are by far the most useful.
Triangle can also have center mesh, center node.
You could, but you don't get anything by that. Even in quad, this node doesn't do anything. Right? This will not change your.
The completeness, you are saying completeness in terms of partial triangle.
Yes. Completeness of an element is the highest degree of complete polynomial.
So this will affect the quality of interpolation.
Yes, this will affect a convergence of your finite element and accuracy, error significantly.
Right.
And here's the and here's how.
But how will they do that? How will you determine the accuracy? Because if you document is complete, let's say in K,
Yeah.
then the interpolation is more accurate.
Your results will be more accurate.
But results will depend on the interpolation, no?
Yes.
The quality of interpolation.
Yes. This is what I'm going to. Well, we're a bit running out of time. So, what do you think? Should I finish finite elements today, or should I leave it for?
You have 10 more minutes.
You think so? Okay. So, what is accuracy of a finite element? We want all numerical results are wrong, right? You can have you're solving numerically, so you're not getting exact solution. You're getting approximation, but how wrong? First, we need to find out how do we measure the error, and one of the best ways, right? You can try maximum difference, but you'll find that is not working well because it could be big error somewhere, small error somewhere else. The best way is to define a norm and then compare norms, well, of the solution. but you need to see what happens with your solution as you refine the mesh. And here's how you refine. This is just a sketch, right? Well, how you get from 1 triangle to 4 triangles, and your mesh parameter h has gone down by half, and here 2, right? So if I have elements who are not regular, I would define mesh parameter as for each element I would define h as smallest circle that encloses the element, and I would take the say as a mesh parameter you can take the average value, but you can still refine this mesh, right? This is the same thing that I've done before. It's just that now I have curved elements. This is the same thing that I've done here, right? So from 1 triangle I can always make 4 easily in this way. So the question is, as I decrease my mesh parameter h, how does the solution behave? Well, first, error has to go to zero, but how fast? But first, what is error? Yes. Let's consider, well, exact solution, which we don't know, but let's assume that we do, u, and finite element solution, uh. The m norm of any function, whether it's well, finite element or is square root of the integral, and here I have the sum of the squares up to mth gradient. Clearly that is always greater than 0, and clearly that has to be less than infinity, that has to be finite. So notice that if I do u naught, that will be measure of displacements, but if I do u1, it measures together displacements and gradients, that is strains. Now I define error as the difference, as the norm of the difference u minus uh. So this is the exact, this is the approximate parameterized by h, mth norm. And the theorem, celebrated finite element theorem, says that this behaves, well, this is proportional to the norm of u, but this behaves as some constant, as h over L, and L is the size of the domain, so cube root of the volume, for example, number of dimensions, well, depends whether you're working 2D or 3D. So this is the size of the mesh, h is a mesh parameter, k is completeness, and m is the norm degree. Sorry? This is finite element solution obtained with the mesh which has parameter h. So the relative error is the ratio of the absolute error divided by the value, right? So the relative error is proportional to h over L to k plus 1 minus n. So let's look at the linear elements. Well, completeness is 1, so I have 1 plus 1 minus m. So that's 2 minus m. So for displacements, R naught is 2 minus 0. I have quadratic convergence. Now, this relative error, we've seen that norms, one, have to do more with strain. Errors in derivatives are always much larger than errors in a function. Right. So this is practically the measure of error in strain. So my strain will converge as k plus as a linear function of h over L, which is rather slow. This is typically considered not good enough.
Small u is the means the real solution.
Yes. Yeah, this is the exact solution, and this is finite element solution.
Exact solution from experiment.
No, theoretical exact solution. We see when you do numerical method, accuracy, what we call accuracy of numerical method, it has to do with numerical method matching the math. Now, there is a whole another story between math and experiments, right? We say that our numerical solution is good if it matches the exact mathematical solution. Okay. So, and for quadratic elements, k equals 2, the error in displacements will have cubic convergence, and the error in strain or stresses will have quadratic convergence. And that is the power of the finite element method. No other numerical this numerical method where we know that if you refine the mesh, you will approach your these are strict mathematical theorems.
So quadratic elements will converge faster.
Yes, yes. Okay, and this is probably a good place to end today's lecture. Next time I will show you a few examples, and we will derive equations for fluids, and I will give you next test problem to work on COMSOL. So if you have not looked at that tutorial, please do so. Well, by tomorrow I will try to give you something a little bit more complicated to work on.
You can ask some questions.
Yeah, questions, of course. And I promise tomorrow we start with phase field, finally. We are pretty much done with background.
That COMSOL you are saying the reference you are giving us. If you give the name of that YouTube video, that is much better. You have given only reference, means that link we do not have.
Link is, yeah. Yeah, here are the links. Can you show the slides? Yeah.
Yeah, so that is the link which we cannot access that link. And if we have the name, then we can search in the YouTube. Then.
Actually, we don't have the slides. Right?
Sorry.
We don't have the slides.
Oh, you don't have the slides. So, Sanjit, can we send the slides to all participants? Well, at least this slide with links.
Whatever documents you sent to me,
Uh-huh.
I have shared that with them. I have an email today and it goes on.
Uh-huh.
You may have already had.
So you have link in the slides, and worst comes to worst, take a photo now, right?
These slides are different, then it will be there in the YouTube after some time. Or
But could you click on that YouTube link?
now maybe.
No, you can. I mean, the second one.
Well, I don't have internet right now here.
Oh, there's no internet?
Yeah. Well, I didn't connect to. well, to any of those, I probably need a password.
Google, we can help if you want.
But it
Anyone. They will
so do we have this TGH internet here?
go on first. Go on.
Here. No, go to the arrow, and the globe. Yeah.
This is showing.
Okay. Okay, so if you click to this one, that's the console website. And it's a text to read, right? And it tells you how to input diffusion type equations into COMSOL. But maybe oh, okay. So that's but it tells you which menu to open or how to select what to do. But the for us more useful one is the this YouTube tutorial because we want to use equation-based modeling. And this is okay. There is what's happening with the sound. Okay, I'm not transmitting sound, but this fellow who posted this is showing you in details what to input into COMSOL. Well, somewhere here we will see COMSOL. Okay, how to write the equations for input in COMSOL, and then you have you open COMSOL interface, how to input them, and so on and on. Right, step by step is what is guiding you through the problem. And it's total, I think about 15 minutes. Yeah, 14 minutes here. So he's showing you what to click, how to open the interface. Very good tutorial. Any more questions? I know I have dumped on you a lot, but please try. Right, you don't have to understand everything. Just try to understand what's going on. We have no choice, right? If you want to get there, there is a certain way that we have to go through. Right, we have to first cover continuum mechanics to do phase field. But next week, no, next week, tomorrow, we are finally starting phase field. And our microstructure problems, which you will find more interesting than everything that I've been talking about so far.
Flex field can be implemented in console or some other software?
Yes,
It can be.
yes, yes. Okay, that's it for today. Thank you.